a shame, that's all. Truth is I love you more than I wanted to. There's no point in trying to pretend. There's been no one who makes me feel like you do. Say we'll be together to the end. But I could leave, but I won't go. It'd be easier, I know. I can't feel a thing from my head down to my toes. So why does it always seem to be me looking at you, you looking at me? It's always the same, it's just a shame, that's all. But I love you more than I wanted to. There's no point in trying to pretend. There's been no one who makes me feel like you do. Say we'll be together to the end. But just as I thought it was going alright, I found out I'm wrong when I thought it was right. It's always the same, it's just a shame, that's all. Well, I could say day and you say night. Tell me it's black when I know that it's white. It's always the same, it's just a shame, that's all. That's all. Curious thing, make a one man weep, make another man sing. Change your heart to a little white dove. More than a feeling, that's the power of love. Tougher than diamonds, rich like cream, stronger and harder than a bad girl's dream. Make a bad one good, make a wrong one right. Power of love that keep you home at night. Don't need money, don't take fame, don't need no credit card to ride this train. It's strong and it's sudden and it's cruel sometimes, but it might just save your life. That's the power of love. That's the power of love. First time you feel it might make you sad. Next time you feel it might make you mad. You'll be glad, baby, when you're found. That's the power that makes the world go round. And it don't take money, don't take fame, don't need no credit card to ride this train. It's strong and it's sudden, it can be cruel sometimes, but it might just save your life. Love is there, yeah, when it gets on you. And with a little don't need no credit card. Ride this train. Tougher than diamonds and stronger than steel. You won't feel nothing till you feel. You feel the power. Just feel the power of love. That's the power. That's the power of love. Feel the power of love. Feel the power of love. Feel the power of love.
Lost in a dream, I don't know which way to go. Let me say it. You are all that you see. Then maybe I'm moving way too slow. I've been fooled before, wouldn't like to get my love caught in the slamming door. How about some information, please? Straight up now, tell me, do you really wanna love me forever? Or am I caught in a hit and run? Straight up now, tell me, is it gonna be you and me together? Or are you just having fun? Time's standing still, wait for some small clue. I keep getting chills when I think your love is true. I've been fooled before, wouldn't like to get my love caught in the slamming door. How about some information, please? Straight up now, tell me, do you really wanna love me forever? Or am I caught in a hit and run? Straight up now, tell me, is it gonna be you and me together? Or are you just having fun? You are so hard to read. You play hide and seek with your true intentions. If you're only playing games, I'll just have to say, do you love me? Do you love me, baby? Do you love me? Do you love me? Hey, baby. Do you love me? Do you love me, baby? Come on now. Do you love me? Do you love me? Tell me, baby. I've been a fool before, wouldn't like to get my love caught in the slamming door. Are you more than hot for me, or am I a page in your history? Oh, I don't mean to make demands, but the word and the deed go hand in hand. How about some information, please, 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 please? Straight up now, tell me. Tell me. Straight up now, tell me. Tell me. Straight up now, tell me.
Makes me feel like do say we'll be too.
I really wanna love me forever. Or am I caught in a hit and run? Straight up now, tell me, is it gonna be you and me together? Or are you just having fun? Straight up now, tell me, do you really wanna love me forever?
Fashioned by fate, suffer so hard from the games played once too often. But making mistakes is a part of life's imperfections. Born of the years, is it so wrong to be human after all? Something about you, baby, so right. I wouldn't be without you, baby, tonight. Did you feel million things and a perfect dream of life? Gone, fragile but free. We remain tender together, not so in love. It's not so wrong. We're only human after all. Please change.
Hello. We're ready to begin the next presentation. Please have a seat.
Tapping on a microphone is not good for its health. Testing. All right. Let me check switching slides here. Okay, that works.
Hey, Bert, what you working on?
Well, I'm working on this presentation, but it's been a while since I've done one with a live audience as opposed to being able to edit out my mistakes. So we'll see how it goes. Okay, so are we ready? All right. I always start out my videos when I say, hi, my name's Jeff. I'm from the Ozark Mountains in Missouri. The rest of the story, as Paul Harvey used to say, is I grew up about, 15 miles up Route 68 here in Champaign County. So you notice on the little blurb that they said I was from Woodstock. Yep, that's where I was born. So, but I spent most of my adult life down in the Ozarks. And I started the videos that way because I didn't know what to say for the life of me on my first video, and that's what came out of my mouth, and it stuck. So what I'm here to talk about today is repairing our vintage computers, and we all kind of probably got back into it the same way, right? You're like, oh, I had that computer as a kid. I wanted that computer as a kid. You find the computer, at your mom and dad's house in the attic or something, and it doesn't work. You buy it on eBay and it doesn't work. And then you jump on the forums and you're like, hey, I've got a black screen, or I've got garbage on the screen, or whatever. And there's a lot of people try to help you. And sometimes it's helpful, and sometimes you get things like, hey, I had something like that, and I replaced, chip M7. And you wind up kind of taking this Easter egg approach, like with old vacuum tubes, and just replaced a bunch of parts, and hopefully it'll work. And that pains me to see people struggling like that, especially because even if you're used to soldering and desoldering, anytime you take parts off and on an old circuit board, you run the risk of damaging something. And if you're not familiar with it, if you're a beginner, that is a really high risk. So the more we can do to make an educated guess as to what the part that's bad might be before we start taking stuff off the board, usually the better off we are. So the technical term for this is a systematic approach, which just means doing something logically, starting in a logical order that'll hopefully lead you to where you want to go. A good example is when you lose your car keys. Rather than running around your whole house and property looking at a random spot for your car keys, you start from the beginning. You're like, oh, okay, I came in with the groceries and I unlocked the front door, and you go look in the front door and you didn't leave the keys there. But I have done that before. And they're like, okay, I put the groceries away, and you go to the kitchen and you don't see them, and you're thinking, all right, I went to put my coat up. Oh, and then the phone rang, and yeah, I stopped at the kitchen table to take a note, and there you find your keys. So we want to take a logical, systematic approach like that when we're trying to fix our computers. And there's one other thing is that this is just a guideline. It's not like GPS coordinates. We're bound to make wrong turns. That's okay. You can turn around, start over again at a certain point. First thing to start out with is the four senses. This is all part of it. You could say this is part of a visual inspection, but we're using our four senses. But, does the computer smell musty? Does it smell burnt? If it has a musty smell, it might have been stored in a damp location. There might be some corrosion on things. That happens a lot, and that's a very good thing to look for. If it smells burnt, you just got this thing off of eBay and it smells burnt. Somebody might have tried to power it up before, and that could have done some damage. That is very likely. Sense of sight. What do you see on the circuit board? Are there parts missing? Again, with a lot of the used stuff we find, there's going to be parts missing. Somebody may have tried to work on it before and not done a very good job. And there can be stuff out of sockets, bent pins on chips. There can be bent pins on chips from the factory, and it made good enough connection to work for years that way. And Sound, when you get to the point of turning it on, does it beep and boop when it's supposed to beep and boop? Sometimes like on our Model 100s here, even if nothing's on the screen, you can type in beep. And if it beeps back at you, you know it's running. It's just not displaying anything. And the sense of taste. Yeah, okay. Don't taste your old computer, okay? I've been tempted, like, I don't know, is that like battery leaking or whatever, but I've fought off the urge so far. The first set of checks I always do, I call PCR, power, clock, and reset. These are the big three that the computer has to have to run. And if you don't have these things, it's not going to run. Power, of course, is the one most people are familiar with. That's plugging into the wall. You may have an internal or external power supply. They can look something like this. I think this is from a Coco 1. Correct me if I'm wrong. Coco 3? Okay, I know it's from a Coco. Forgive the blasphemy. C64 type external power supply. The thing is, they come in different shapes and sizes. They will have different output voltages. They may take AC in and give you DC out. They may give you AC and DC out. So it just depends on the particular computer that you're looking at. Ideally, we would test these power supplies without them connected to the computer, but under load. So we can make sure they're working good before we plug them into the computer. Sometimes that is really, really tough. There's some old computers where the power supply is built onto the main board and you can't disconnect them, right? And you've got some of these RAM chips will take 5 volts, plus 5 volts, minus 5 volts, and 12 volts. And when the RAM chips go bad, they tend to short all 3 rails together. And you don't want to send 12 volts into the rest of your 5 volt components if you can avoid it. But ideally, if we can, at least unplug it and check it to make sure the open circuit voltage looks reasonable. If you can't do anything else, that's the first step. Clock. There are all sorts of different clock circuits. You'll see this type of circuit with a few inverter gates in various types of old equipment. It looks very simple. Sometimes people say, well, can I test here at the crystal? You can't test at the crystal. You'll load this down. You have to test somewhere like here with a proper piece of equipment. Clock circuits can vary quite wildly. On the Model 100, this is an 80C85 processor. It has the crystal driving circuitry built into the processor. So it's just hanging off the end of the processor. So there's not a lot there to go wrong. If the crystal's good, there's not a problem with the caps or traces or something like that. There's nothing left but the processor. And you'll see, if I didn't cut it off in this picture, yeah, I did. I don't see the clock out. Anyhow, there'll be a clock out of there to the rest of the system. And it can go all the way to some really confusing stuff like this with lots of different clocks and a PLL circuit made out of discrete components. Again, sorry, it's a C64, but this is kind of representative of what you see in a lot of things.
Check, check, check.
Okay. All right. Yep. See, it's always the power. Yeah. So clock circuits can vary wildly. It's the type of thing you may need an oscilloscope to check. Some meters will have a frequency check function, which is a whole lot better than nothing. But if the clock isn't running, the computer's not going to running. This is like the drum beat that everything else follows. So it's got to be there. Reset. This is another big one. Again, I think this is a Coco one. Correct me if I'm wrong. This is a very simple RC circuit. There's not a lot that's going to go wrong with that. This may not be adequate for every system that's out there. You can have systems like our C64 that'll use a 555 or 556, and there can be everything in between those two things. On our Model 100, the reset circuit is very complex because it's integrated in with the low power shutdown. It's got some extra stuff it's got to worry about to make sure that the battery back RAM is starting up properly and not getting scrambled. And it also has the auto power off to be concerned with. So this whole block highlighted in yellow is all the reset circuitry. And it ties in through this transistor here up to the power supply where it can shut the power supply down. There's a lot that can go wrong there. Now, as an example, when I got here today and I hooked up all this mess to this Model 100, it did not work. I got my multimeter and I checked power. The plus 5 volts and minus 5 volts were just a little low, about 4.85 volts, not too bad. You know, still where I would probably think that isn't the problem. I checked the reset circuit. It was held low. So I'm like, okay, slightly low voltage, reset circuit held low. It's probably a power condition. This thing is sensing the low voltage, which is kind of done up at the top here. I've kind of cut off in this picture. And sure enough, the rechargeable lithium batteries I put in it, one of them was bad. It was really hot. Took those out, threw in some regular alkalines. Everything was fine. Some common faults, like in a reset circuit, I've seen bad capacitors, leaking capacitor. It's not timing right. You may get a varied reset pulse. Sometimes it may work. Sometimes it may do silly things when it starts up because that reset circuit is telling all the chips connected to it, we're just starting out. They're going to reset all of their registers to a known state. So when everything starts up, it's going to work properly. Without that, everything is starting up, all the registers in a random state, and it may do something silly. It may not work at all. It may be a black screen or a gray screen or whatever the color of the screen is where things aren't working right on your particular computer. The next step, if our first step of checks didn't reveal anything, is BADS, bus address decoding and chip selects. The address and data bus has lots of different chips connected to it. And they all have to share and they have to play nice with each other. And they often don't do that. And you can imagine being in a room with 100 kindergartners all screaming at you at the same time. That's what the bus can be like if things aren't playing nice. So the job of the address decoding is to look at what the computer's trying to talk to interpret all those signals and say, oh, I'm trying to talk to RAM now, right? Or I'm trying to talk to this IO chip, or I'm trying to talk to and scan the keyboard. And if the address decoding is not working right, it may select the wrong chip at the wrong time. And of course, something silly is going to happen. So the address decoding is giving us our chip selects. And an example here is on our Model 100. We have our 8085 processor. We have our lower address and data lines. They're labeled 80 through 87. Are feeding over to some latches as well as the upper bits. Now, in this particular processor, it gets more complicated because it's sharing the lower 8 bits of the address bus with the data bus. That's called multiplexing, and it just means they're using the same pins at different times for multiple purposes. And it makes our jobs trying to figure out what's going wrong harder. Because we'll have all sorts of these latch chips that are like taking a snapshot of the bus activity at that particular slice of time to save it for whatever function is going on. Like it might be trying to scan the keyboard. So it's going to say, here is the row I want to scan, or the column I want to scan, in the case of the M100, as I recall. And so the latch chip is going to keep that there, and then it's going to read from the rows right? And you can't hang up the data bus for the column, so you have to have that latch in there. And this was about 3 o'clock in the morning. I couldn't sleep one night, and this particular machine, I had completely missed this problem earlier in the day. And like I said, there's no GPS to guide you. I had to back up, go back to basics, look at all these things, look at all my address and data signals with the oscilloscope. And I saw this signal with this little spike here that looks really odd. That is the result of that multiplexing I was talking about. When it's deciding it's going to change the purpose for those pins, you might get really odd things like this. Even on other parts of the system where you see a chip changing functions on part of the bus, you'll get a little spike like that. It doesn't matter because the computer's not trying to read anything from the data bus or address bus at that time. It's like if you stuck your tongue out at your teacher, as long as she didn't see you, it didn't matter, right? But if she's looking, if the computer was looking for something right here and this tongue was sticking out, bad things are going to happen. This particular top trace with this stair-step effect is what's called bus contention. Two things are trying to talk on the same line at the same time. And when I actually made this video, I said bus convention, and then a few minutes later realized that I said the wrong word. And, you know, just based on the functionality of the machine, this is really hard to tell what's going on. The only way that you can really do it is using the oscilloscope and taking a look at all the signals. And when I get a weird problem like this, I'll look at all the address lines, all the data lines, and make sure it looks reasonable. I don't know that it's correct. I don't know what it's doing or what function it's doing, but I know that it's not this. And interestingly, on this particular machine, it mostly worked. And why won't it let me play this? Will that do it? Yes. So you can see the corruption that's on the screen. There's some missing spots. And if it'll let me skip forward. Yeah. Anyhow, this was a really odd one because the machine mostly worked, but there was graphical corruption, and you normally think, hey, this is a screen problem. It's an LCD problem or something like that. When I noticed that bus conflict, I went, and sometimes you can say, okay, it's these two particular data lines, right? What chips have those in common? And you can kind of narrow down what the fault might be. In this particular case, it was like between lines, address data lines 2, 5, and 7, and which go to everything. So then my next step was, well, okay, what is the easiest to pull out of the system, right? I don't want to pull the processor because that's difficult. There's a lot of pins. Well, there was 2 latches, neither of which was required for the computer to run. One was for the keyboard, one was for the RS-232. I pulled the keyboard first, still did this, pulled the latch for the RS-232 port. The screen was fine. So sometimes when you get down to an either or thing, you go with the easiest solution first. You know, if the 16-pin chip or 14-pin chip can be it just as likely as the 40-pin chip, the smaller chip is probably cheaper too if you mess it up trying to take it out. And it's certainly easier to pull. When we get to stage 3, when none of these things will work, this is where you get into the really crazy stuff. And unless we've already gone through stage 1 and stage 2, none of these things make any difference. So things I'll see on the forums a lot is somebody will say, I got a diagnostic ROM for my machine, or I got a test cartridge and I plugged it in and it still doesn't work. It's like, well, you know, if you don't have voltage getting to the video chip, it doesn't matter what you've got plugged into it. It's just not going to work. You know, if you don't have a clock or if your reset's stuck, it's not going to work. So this part doesn't matter. When we know we have all those basic building blocks and things look like they should work, we have bus activity, yada, yada. This is when we get into these things. And these can be such a wonderful diagnostic aid. You can get along without them, but there are certain problems that will eat your lunch if you don't have something like this to use, and it'll take you 5 minutes if you do. This screenshot right here is from a little 8-channel logic analyzer. And I had problems with this Model 100. This is the first one I ever got, which was broken because, that's how old equipment is. It's broken. And it would not boot. It wasn't even getting to the point of resetting the LCD, so somewhere early in the boot process. And, there was address and data signals at times when it was trying to boot, so it looked like everything was kind of there, but who knows what it is after that point. And since I didn't have this fancy test harness, which we'll talk about in a little bit, I hooked up my logic analyzer, which is only 8 channels. So I had to use the 7th channel as kind of a sync signal to let me know when the ROM was being read from, because I was trying to capture the signals being read out of the ROM so I knew what code was being run. And then I turned this into hex values in each sync signal and went through a disassembly I found on the line for the part of the ROM for the Model 100 where it was booting, and found out that it copies a little bit of the ROM into RAM so it can run some self-modifying code. And that part it was copying was overriding the stack. So when it tried to return from doing that copying, it went somewhere crazy, and it was a little different every time. And this was very difficult to find this way. This is like the hardest way possible to go about doing that. But it is possible because we don't have testing aids for every mid-inch computer out there. And if you have a analyzer with more channels, it's easier than what I had to go through here. So this is just showing this setup here. This little board here will run a series of tests at a very low level first, and it'll first test out all the RAM chips to see if they're good. And only when it finds at least one good RAM module will it then start running more extensive code that can make use of the stack. Because before that, you can't use the stack. You can't do any looping or anything like that. It's just not available. So it's a lot of boilerplate assembly code, doing the same thing in line to test all that out. And it has this little LCD here that's memory mapped that it can write to as a means of providing output to the user, which is really nice. And something like this, since it does that RAM test to start with, it'll tell you in the first 5 minutes once you hook it up if the RAM module is good. And the RAM modules on these, this one is always soldered in. And on the later machines, these other two might have been. And they're a pain to remove. They didn't do thermal isolation on the pads on these. It makes them really difficult to desolder. I wind up with like a hairdryer type heating gun to preheat the board in that area so you can desolder it. It's very difficult to work on. The other advantage to a test harness like this is you get some automated testing of the I/O ports. This will test the expansion bus, serial bus, the cassette relay. If you hook up a cassette and press the right button at the right time, it'll even check the in and out to the cassette deck. Here I've got the keyboard and LCD hooked up, so it actually has a key test function, and the screenshot we saw earlier was actually the LCD output it does. The way I have this configured here, I'll try to tip this up so everybody can see it. It has a loop back for the keyboard and a little dongle that plugs in where the LCD goes. And both of these are loop backs, so it'll loop the signals back so it can check the signal integrity up to those connectors, which is very handy, especially for the LCD, because the LCD not working is a big problem on these machines. And the guy that made this even put some comparators on here, so it'll check that the voltage is good. At the same time, gives you a quick visual indication. These things can be a big time saver. And when especially when I'm working on somebody else's machine, I like to know that not only what they sent it for is fixed, but that there's not some other problem they're going to find later when I send it back to them. So it's really nice to be able to run tests like that. There are similar things for other computers, from a ROM that'll run diagnostic test and flash the screen or something if it finds bad RAM, or that'll have like an RS-232 loopback, that type of thing. Let's see how we doing on time. Okay, tools. This is I'm really heavily into this. I have a lot of tools dedicated to this part of the hobby of repairing the computers. It's not everybody's thing, and not everybody has all the tools already. So if it's something you're interested in getting started with, there's tools you need to get started, your basic tool set. And there are more advanced tools, that you can add in as you go. The big things are hand tools, multimeter, soldering equipment, and in lieu of a logic analyzer or oscilloscope, a logic probe. Hand tools, most everybody has hand tools. Screwdrivers, a selection of screwdrivers, things like that, wire strippers. None of it has to be fancy. I bought some really expensive wire strippers, which didn't turn out to be that good, and I still use my, cheap $10 set for a lot of things. Multimeter. I've had this multimeter made by Triplet for more than 20 years. It's a decent meter. It's not fancy. It doesn't have a lot of stuff built into it, but it does a good job. A decent meter is your friend, and the cheap $5 meter from Harbor Freight is more like a frenemy. A lot of times they don't work that great, but it's better than nothing. If you're doing low voltage stuff, even a cheap meter will do a good job. When you get into working on mains voltages, a cheap meter can be a bomb in your hand. They don't have good over voltage protection or explosion protection to keep anything going wrong from coming out of the case into your hand. There is a thread on the EEV blog forum where guys go through and review meters. And I mean, you can get a really, really, really good meter these days for less than $50. So you don't have to spend $200 or $300 on a multimeter. You can get a really good one for that price. Component testers. This component tester I bought as a kit for like $10 several years ago. There are much fancier ones now that have a graphical LCD, and they come with a case for $20. These are the type of things, it's like a no-go tester, right? You've seen in manufacturing where they'll have two different size pins and one should fit in a hole and one shouldn't. That's kind of what this guy is. I compared this to some of our fancy capacitor testing equipment at work, and it was within a few percent for things like ESR. So good enough, because what we're going to find in our old equipment, when the capacitors go bad, the ESR is out in left field somewhere, right? The capacitance is way off. We're not looking for, a 0.5% variance in what the rating was for a specific capacitor, when we're testing it for manufacturing or something. I actually did a whole video where I troubleshot my espresso machine using nothing but this, just to see if it would work. And it actually did a good job because it'll do, like small SCRs and triacs and things like that. So I was surprised, but it did a good job. Yeah.
What kind of components is it?
It will test. You just hook up the leads. You like it to a transistor. You hook up the 3 leads, and it'll look at it and go, "Oh, that looks like a transistor." You hook up 2 random leads to a 2-lead component, and it'll look at it and go, "Oh, that looks like a capacitor of this value with this ESR," or it looks like a resistor, or it looks like a diode that's polarized this way. So, like I said, not the most accurate thing in the world, but boy, is it handy. Now, a lot of times on your multimeters, it'll have a diode mode, and you can check things like that. But this will do it really fast, and it's a good enough answer for our purposes. Logic probe. This was purchased at Radio Shack in Marysville, Ohio in about 1984. Still have it. Still works. It's still handy. Even with fancier tools, it's handy because it's quick and it's easy and it tells you the answer that you need. This, you hook it up to power it from your circuit board. You poke this thing onto the signal that you're wanting to test, and it'll tell you if it's high or low or changing. And a lot of times, that's all you need to know. And they still make models that look exactly like this. Soldering, you kind of get into an area where you can spend just as much money as you want to spend. This was bought about the same time. This is a solder sucker. You push that down. You heat up the solder with your soldering iron, and you do that to suck it up. This is an okay one. Of course, I wore it out, and this has parts in it from a newer, cheaper plastic version. It wasn't very good, but I was able to scrounge the parts to fix this old one, and it still works okay. It's still sitting right out on my bench because I use it on occasion. There are versions of this that have a silicone tip that actually work really good. You know, and it's something that's like less than 20 bucks. So if you don't have the money for a, vacuum desoldering tool, that'll still do the job. There's also solder braid, which is like a flat copper mesh wire with some flux inside. Even if you have fancy desoldering tools, that should still be on your workbench. It'll get blobs of solder off of surfaces and things and off of pads and make it nice and flat. It's great stuff. Yeah. Yeah, it's one of those things you got to try to hold it and use it at the same time, and that can be tricky. Sources for tools. There's places like, I think this was from Adafruit. It's a kit they have with some basic hand tools and, a cheap meter and soldering iron that's decent, right? If you don't have anything, you can pick up a kit like this. It'll get you started and, let you put some things together. My kind of basics for a soldering iron is to be temperature controlled, temperature adjustable. The temperature control kind of depends on the quality of the iron, but again, there's some really decent ones now for not a lot of money. You don't, how do I say it? The easiest way to really mess up your circuit board is to use a really shoddy soldering iron, because you won't be able to, transfer the heat properly, and you'll wind up overheating the joint trying to get it hot enough just to desolder. So it's a good thing, to spend a little bit of money on. The thing with a kit like this from like Adafruit or SparkFun, normally you can have a higher confidence that the stuff is okay. It's a decent quality. It may not be the best stuff in the world, but it's decent than if you buy something random from eBay. Because these guys want to protect their reputation. And they're, yeah, they have a whole selection of like really good irons for less than 50 bucks. When we get into advanced tools, you have things like an oscilloscope, the logic analyzer. This is the one, I don't know, this is like 10 years old. It was about $100 at the time. It's 8 channels. It's USB. It does the job. There are clones of this because they use basically an off-the-shelf IC and wrote some fancy software to do all the stuff. The software is wonderful. This is a Saley. So somebody cloned the hardware. And you can get fancier desoldering tools. But even still, the solder braid is a great thing to have in your toolkit. Oscilloscopes. This is another tool you can spend as much money as you want to spend on. And they can be super, super complex to operate because they can do all sorts of things now. They just have everything built in. Do all sorts of math on the signal, have multiple channels. This is a cheap 30 megahertz one I bought on sale for $200-ish several years ago. I still keep this one because it's battery powered. It's got a battery in it. And if you're working on like switch mode power supplies, you don't want your oscilloscope plugged into the wall because the oscilloscope ground is connected to Earth. So you wind up shorting out your power supply trying to work on it, which is bad news. So this is, it's a decent scope. It was inexpensive at the time, what I could afford. Before that, I had a Tektronix like 465. It was a portable scope made back in the 1980s. It was only 10 megahertz, but it worked, right? It wasn't fancy, but it did the job for a 1 megahertz, CPU computer. It was okay. Logic analyzers like this, the USB things, these are very inexpensive today. It requires a bit more knowledge of the computer to make sense of what you're seeing, because you have to know what all the signals are supposed to be, but it can be an indispensable tool sometimes. Desoldering stuff. Okay. Heiko makes good stuff, and they have for years. So we have Heiko, and we have Heiko clones, and we have clones of Heiko clones. And they all look the same, right? There are some of the clones that are great tools, and there are some that are a fire waiting to happen. Of course, Heiko's more expensive, but if you ask somebody that's bought one what the quality was like and where they got it, right? And it's a dealer that you're going to get the same thing from the next time, then that's a good way to go. And these are a decent desoldering tool. The thing is, with any desoldering tool like this, you got to clean it. You got to clean it all the time, and you got to keep it clean, or it'll plug up inside, and then you'll be really, really mad at it because you're trying to get something done, and it's completely plugged up with solder. You're heating the solder down here and sucking it up into this chamber, right? And there's some of it's going to hang out right here, right, and not get sucked completely up in there. And then you're going to shut this off, and you're going to have this cold lump of solder in there, and then the next solder you try to suck up is going to get stuck on that. So it's one of those things. If you use it just once or twice, you probably don't, 1 or 2 holes at, today, you might not want to clean it out, but the next time, if you don't start out cleaning it out before you use it, then you might have a problem. So I don't always do that, but it's a good habit to be in. When you sit down, you're ready to work on it, clean out the desoldering tool first, let it heat up, clean it out. Have like a little ramrod, you run down the snout to make sure it's all clean. And that way you're ready to go. A lot of these will have filters. Yeah.
One thing I found the plastic on this gets solder in it, but I use used dryer sheets, and you can put them on your pinky and stuff, and you clean out all the stuff. Not out of the hot part, but of the little plastic attachment. Used dryer sheets are extremely good to clean that up.
Yeah, some of them will have plastic, some will have like a glass tube there. You can kind of clean the inside of that out. If you go off the deep end, like, I don't know, me, you wind up with this guy. Where I used to work years ago had these, right? This is not a new piece of technology. I bought this used on eBay. I waited and waited and waited till I found the one that was in good shape that I could afford. Pace has made this same basic model for 30 years. It used to have a silver front, and some of them had only 2 channels. This is a black front, which is slightly newer, but not a lot newer. But one of the guys from Pace told me that they sold a lot of these to the U.S. military, and so they have a contract. They have to supply spare parts for an enormous number of years. So they make a newer version of this, which is better. But you can still find these. You can get all the tips for them. And I look on eBay for tips when they come up for a good price, and I'll buy the tips. Right now, I'm waiting for a spare heater to come up for like the desoldering tool. Because I don't want to spend $100 to buy one from Pace. I'll wait till somebody has a new one in old stock on eBay for $30 and keep it on hand. A rework station like this, it'll control, 1 to more irons at a time. I usually only have the soldering iron and desoldering tool plugged in at one time. This is like this one is like a tweezer type tool. So for like surface mount, chip parts, super quick to get stuff off. And this is like for like quad flat packs and things like that. And they have various types of tools, but these are really the only ones that are important to me. But that's on the extreme end. The newer models, even newer models with soldering irons, will have the heater cartridge and tip built into one unit, which seems like a ripoff at first. But the heat transfer on something like that is a lot better. And these control the temperature really well, so the tips last a long time if you keep them clean.
Yeah, you've seen the new model.
The new pace, yeah.
And in your opinion, are there things that you do with this one that you can't do?
The newer ones, it'll go up to a little higher temperature to deal with all the unleaded solder. And they have the one-piece tip and heater cartridge, which is better. But like a new one, a 3-channel pace like this, the newer style, is going to start about $1,500. So yeah, that was out of my price range. So, I found this on eBay. I don't know what the story was, but it looked like they used it twice. So yeah, it was in the original box and everything. So it was like, okay. But that's the type of thing, if it's something you're interested in, you just got to wait till it pops up. Okay, what about questions? And then I'll show off some more of this stuff.
Do you think that the tip is important or soldering iron, different tips?
Different tips, yes, that's a very good question. Tips come in all shapes and sizes, and it's a darn good thing. Heat transfer, right, is about the surface area of the tip and the solder on the tip. You'll see some old guides to soldering, which are written by people that never soldered in their life, I think. They'll say, put the soldering iron on the joint, and then after the joint heats up, press the solder into the joint. That's ridiculous because you have no heat transfer. You need a little bit of solder on the end of the tip so you have good heat transfer. And so you'll see me a lot of times on the video, and I'm not thinking about doing it. I'll put a dab of solder on the iron before I go to the joint because I know I need some good heat transfer there. A wider tip will give you better heat transfer. Yeah. So yeah, I use the one I have in most often is probably about a 3 millimeter wide chisel tip. I use that for most through hole parts. There's some things that's a little too big for. I've been building a lot of the backpacks my friend designed recently, which is an SD card storage for these Model 100 type computers. And for a lot of the joints on those, I'm using a fine pointed tip, a conical tip, because it works better. But my preference is for the chisel tip. For really big joints where I need to get a lot of heat into it, I'll use a wider chisel tip. For the desoldering tools, you have different size orifices in the thing. For the tweezer types, there's different width tweezer tips, things like that. And you get the fancier ones where it'll do all the quad flat placket ones, and there's different sizes there. But yeah, a good quality tip, right, in different sizes, in different shapes. The chisel tips are probably better, I think, for most things. The pointy ones do have their purposes, though. Yeah.
I was wondering, when did you get started with this, or what got you started? Is this something you did professionally before another more modern systems, or you just?
I went to a small school system. There was about 60 kids in my class. So we had a Model 3. I was thinking it was a Model 2 earlier, but it wasn't. It was like a Model 3 TRS-80 and a few Ataris. That was all the computers we had in the entire high school. There was none in the elementary. And I got to fix those because, I said I could. I didn't know anything about them because that was the first time I touched a computer. But, it's like a mechanical electronic thing, okay? You just, yeah. I had a few computers at home which I had to fix. I remember probably about 1990 doing a memory upgrade on a Coco where the Radio Shack had bought the bad 32K RAM chips and disabled half of it, and so you could buy a good set of RAM chips and take the old ones out. So that type of thing. I have done it professionally, like electronics manufacturing and board repair and things like that. And this, I kind of got started again because when my dad passed away, he had all of my old Commodore 64 disc and books and things along that line. The computer was long gone somewhere. But I got that stuff, and I was like, oh, I want to be able to read these discs. So then you got to start buying the computer and the disk drive, and yada yada. And then the power supplies are junk, so you need a new power supply. And I wound up like picking up this Model 100, which didn't work. And then I just started doing the videos because I wanted to share, what I had learned over the years with other people, and maybe saves people some hassle to like randomly swapping chip after chip. Because the problem with swapping chips is you may not know if okay, I'll take this chip out of this board and plug into this board, but is that chip bad? You can have a marginal chip that'll kind of work in one board. Crystals will do this. You can have a crystal that'll kind of work with one clock generator chip, but not with another. And actually both chips are bad. And it can be very confusing if you're just swapping parts around, trying to figure out what's going on. Any other questions?
Yeah, I wanted to thank you for mentioning putting some solder in the iron, but not so much a question, but maybe you can describe, like when you're doing desoldering, you need to do the same thing.
Yes.
You can't just turn that thing on and start pulling, so go ahead.
You let the joint heat up.
Preheat it with some flux?
Yes. Oh, thank you. I forgot to mention flux. Flux is your best friend when you're soldering, whether you're soldering or desoldering. It not only removes some of the contaminants from the joint, but allows the solder to flow out nice and even. And I almost always put some flux on the joint when I'm heating it up. It'll allow it to flow out, especially if you have something where like we've had a capacitor leak or something like that. Well, now you've got a lot of corrosion on that joint, a lot of crud mixed in with that solder.
Yeah.
Yeah.
Do you use deoxit?
Yes. I use a combination. I have some electronic cleaner made by CRC that I use just to clean stuff out. Then I use deoxit to remove oxidation. There's some types you can get that has like lubricants for switches and stuff like that in it. So that's really good. But yeah, deoxit is another one of those miracle things that can solve a lot of problems. It's not the cure for everything, but it's good to have on hand.
How much space is your work area?
It's my basement, basically. I live alone, kids out of the house. So yeah, no, it's fine. It's so much fun, right? And there's so much stuff that, when we were growing up, right, you saw this stuff in person, but there's so much more than, we knew about at the time.
If you want to learn a little more about the tools and techniques of using the tools, are those things that you cover on your YouTube channel, or do you have any recommendations for places to go?
I do cover a lot of that. Thank you for asking that. It's part of it leads into a question or a point I wanted to make. If you're just getting started and you want to, work on your old computer, do something you don't care about first. I can remember I went to a vocational school and studied electronics, and our instructor had this pile of old circuit boards from something, and that's what we learned to solder and desolder on, because if we screwed it up, it didn't make any difference. That's a good way to do it. There's a lot of kits out there now. Soldering together a kit is a good way to do things. You see some things that'll be like, okay, you have this Arduino board and you build the shield that goes on it, right? And you hook up some wires. I have a friend that just did that with a SD card storage solution for an Epson PX8, I think it was. It was like the first time he had done that, right? And he made a few mistakes here and there. But, part of it was like building with Legos, right? Just plugging stuff together. And part of it was he had to solder things together, right? And figure out how you wire a switch in series, which may not seem that complicated, but if you've never done it, you don't know what the terminology is, right? Somebody tells you to wire it in series, you're like, what does that mean, right? So yeah, that's a good way to start out. There's so many good resources online now. And you'll find with soldering, it's kind of like a religion. No matter how you do it, it's the wrong way to somebody else. My advice in my videos when I'm soldering is I tell people it's not a race. Some people want to get the iron really hot and like dab it on there in 1 or 2 seconds. And that's not enough time to heat up the joint to get everything to flow off of there. So, in production, when these boards were going through a wave machine, they weren't on there for 1 second. All right, they're going through and they're preheating and they're going through this wave of solder like this, first through flux and then through solder. So they're warm for minutes at a time, even surface mount stuff, right? That's probably a 5-minute cycle or so. By the time you preheat the board, you let it soak, you get that last little bit of heating, the solder reflows, and then you start cooling it down. Yeah, that shock heating is actually not very good for most electronic components.
Is there any particular brand of solder you recommend for electronics?
No, just I tend to get like Kester or something like that, a brand I know. There's a lot of interesting no-name brands available now that I don't know what they're made out of. Depending on the solder you get, you can get a solder with a rosin flux, and if you use additional flux with that, use rosin flux. You can get solder with a no clean type of flux built in, so you need to use a compatible flux with that. I really don't like the no clean flux. The fumes are terrible. Rosin doesn't bother me a bit. Rosin is like made from pine tree pitch or something like that. So,
What do you think on oscilloscopes, analog or digital?
yes. Digital scopes like this, even though this is a cheap one, right? It does a good job. This is better than the 10 megahertz Tektronix I had, right? It does the job. It'll do things it wouldn't. I'm not married to either one. These are smaller and lighter and cheaper now. And a lot of the newer ones, they'll have you can vary the persistence of the signal and keep it on there really long and get nearly the same effect you could with an analog scope. So again, if you get a chance to buy a scope and it's an analog scope, that'll work just as well. So, use the tools you got, what you can get a hold of.
You wear any device straps?
Sometimes. It depends on what I'm doing. I have a grounded ESD mat that I work on all the time, and I don't fidget. I saw this guy online. He's like, if you're sitting down at your bench and then you jump up like this, you can generate this huge ESD spike. And I'm like, why would I do that? Because you're moving really fast off of your seat, right? You've got that sudden friction right there, sudden separation. Yeah, you're going to generate a voltage, but it's like I don't have the need to jump up out of my seat that fast. I'm not on fire. So there are, especially old CMOS chips are very, very static sensitive, and you got to be very careful. But other than that, I'm in the habit of, I've got my ESD mat there and I'm touching it all the time. And I'm not, some people, I worked with a guy one time, we were working right beside each other, and he could zap a circuit board every 5 minutes in the same environment, right? And it's like, I don't know what you're doing, Todd. What are you doing? Probably, other than having the strap, just safe working practices. Okay, how are we doing on time? I don't know because my computer's not showing me the time here. Oh, okay. So no more questions. Okay, let's back up through the slides. Let me see if I missed anything. Yeah. Wrong button.
Wrong place.
That's for the practice.
What is it doing?
How much was that thing?
That was radio check.
Yeah. Okay, I'll talk about this test harness right here. I'll have to do it one-handed, but this is something a friend of mine made, and it's what, actually, he's a really good friend of mine, but I've never met him, right? Yeah, he lives in California, and we work on stuff together all the time, right? And it's like, we mesh, and so we can do that. He had a few Model 100s that were really difficult repairs. And so he came up with this test harness and wrote all the code that runs on this test ROM. And it, tests the ports and everything automatically. And we were chatting one night and I said, maybe we should do a loop back for this. And it was like in 2 days, he had designed this board and this loop back cable. And, me, all I got done in that amount of time was these 2 little boards, which are just a bunch of connectors. But what these do, and this is, again, if you go overboard with a particular model, these are extensions. There's some cables that go with it for the keyboard and LCD on this because, those cables are about this long, so you can fold it over, right? And if you're trying to see if the LCD is working while you're making measurements on the board or something, you can't do that. So I just made these so I could, have another 12 inches or 20 inches of cable in there and have the test points right on the boards. It's made it, very handy. And you'll see people have developed whatever type of computer you've got. There's people who've developed similar things for those.
How big is the Model 100? It sounds like you're preparing on something pretty large. The community Model 100?
Yeah, they were made by Kyocera in Japan. And, it includes the Model 100, 102, the Olivetti M10, which is the Model 100 board, slightly reconfigured. All the component names are even the same. Same leaky capacitors. Oh, that's another subject, leaking capacitors. There's like a religious sect, right? You got to recap everything. Yeah. On the Model 100, that's true. 90% of these capacitors on here are leaking. That's what they do. Especially there's a lot of little 10 microfarad caps in the power supply, over here. And the bad ones will eat into the copper. Yeah. Can make a mess out of thing, eat the traces away. So this is one of the few computers that I will recap off the bat. The Olivetti M10, same age, same design, same capacitors. T102, those are fine. I've not seen one that's had a problem yet. The NEC, the 8201, those, haven't seen a big problem with those.
So you primarily work on portable?
Know about everything. But I don't know why exactly I got so interested in doing these, other than this first one I worked on was such a pain to fix. It was like a great sense of accomplishment that I got it to run, and there are a lot. It's actually a really good computer to use. Yeah. The keyboard is fantastic. I think the set of features that it had on it for that time period were really well thought out. Compared to like similar models like the Convergent Work Slate, which had a ridiculous keyboard. It had some really cool features like built-in microcassette, which could also be an answering machine. But the keyboard was stupid. Nobody wanted to type on it. But these were, some people use these today for writing on because it's such a fantastic machine.
What about the LCD screen itself? Is it hard to replace?
No, it plugs in. There's a few chips on there which are they're similar to standard LCD driver chips of the era, right? But they're in a different package, so that's the only place you'll find them. Sometimes those fail.
Usually it's the battery corrosion that is killing the thing.
I've had one bad LCD glass on a T102. The interesting thing is they're completely symmetrical, so you can take the glass out, rotate it 180 degrees, right? Plug it back in, get your zebra strips lined up, and it'll still work. It's pretty amazing. And I'm not sure, I'm about 50% sure it's the same glass as on the Model 100. It's just a slightly different housing. Yeah, but there's no replacement glasses. You're going to, if you have a bad LCD, you're going to get it out of a donor machine. There is a guy working on replacement zebra strips, though.
Yeah, they haven't been completely figured out yet. So, because what happens is the zebra strips are based on silicone and carbonized silicone. So it's basically a whole bunch of layers. That's why they call it the zebra, because it's black is the carbonized layer, and then here's clear, which is an insulator, and then black, and then insulator, black, and insulator. And then it makes a sequence of traces from there go up to a sequence of traces that have been vapor deposited onto the back of the glass. So when you compress the whole thing, the zebra strip tends to take a step. So if you find out that you have to take the glass off or something, or whatever, you have to repair the traces underneath the zebra strip, you really can't put the old one back on again. It's already taken steps off. Sometimes the compression doesn't make it equal pressure all the way across. Somebody was working on trying to make a replacement set of
Yeah,
strip.
it can be a one-time assembly type of thing.
But usually it's the capacitors that leak that cause corrosion that corrode the traces. And then a lot of the times it's the battery operated device, over time batteries can corrode. And since the battery, the display is right above the battery, if the display or if the unit was set on the back or on the side or something, then the corrosion drips on stuff. So that's usually what kills the displays.
Yep.
The battery corrosion drips onto the circuit board and then corrodes the traces, and then you can't easily repair them.
Yeah, so
Especially if it's underneath the zebra strip.
get the darn batteries out. So, okay, thanks. That was this microphone is way too fancy for me.
song playing on the radio. Yeah, the DJ said love's a game of easy come and easy go.
Hello. Hello, test 1, 2, 3. Test 1, 2, 3. Okay. Okay, I think I'm ready to go. Sure. Okay, can you guys hear me? Am I supposed to go? I don't know. Are you ready? Okay. Well, welcome everyone. I cannot see you guys. Lauren sent me a picture earlier, so I have a bit of an idea of the setup that you have right now. Welcome to Tandy Assembly 21. Still a little bit different than we usually have it. My apologies for not being in person in Springfield, Ohio, but I still thought I'm gonna talk a bit about my projects, and I'm going to kick it off with a little presentation on Pocketress. I'm sharing this slot with Matt, who will then, during the second half, talk about his FPGA version of Pocketress. Now, since I cannot see you, I'm totally okay if people ask questions during the presentation, so I just need some volunteer to just shout and interrupt me. So maybe Pete, maybe you can do that, or someone. So again, feel free to ask questions during the presentation. And let me start my screen sharing here. I came prepared. Where is my? Okay, let me see. It's not this one. So can you see my screen? Can you guys see my screen? I'm not hearing anything, so I have no idea what's happening right now. I'm assuming you can see my screen, so I will just start talking. So once again, welcome to my presentation, Pocketress and Other Mysteries. I'm sure you all know the cover. I also had the books back in the days when I grew up in Germany. Pocketress, I had the idea after the last Tandy assembly 2 years ago in 2019. And I began some prototyping soon after I came back from Tandy assembly. And then at some point, Andrew Quinn from New Zealand also then joined the project and helped especially with the PCB layout later. So this, even though he cannot be here right now with the time difference, but I do want to acknowledge his contributions. So what is Pocketris? Pocketris is basically a hardware emulation of a Model 3/4. And I'm using an ESP microcontroller to basically just do everything that the old machine did. Those of you who have heard my talks before, you know that I'm a big fan of these ESP-based microcontrollers. I've used them also for Tris.io, the hardware expansion that I created for Model 3, Model 1. But basically here I'm using the ESP to emulate a complete TRS-80, and it starts with the Z80 emulation. It creates a VGA signal. It has keyboard input. It not only can generate game sounds, but what I'm also proud of, and I hope to show that during the demo later, you can also load cassette tapes from the audio interface. And last but not least, you can simulate, or I'm simulating the old 50-pin I/O bus. Actually, you can see, I'm also proud to announce the next version of Pocketris, update version 2.3, that has an edge connector down here for the 50-pin connector. So you can actually then use the old cables to easily connect to Pocketris. So why do this? Well, it's a low cost emulation. Of course, there are a lot of emulators out there that run on PCs. So why then do this on in hardware? Well, for maybe two serious reasons. You can use it to test the environment for I/O bus. So you can actually connect some peripherals here and then use Pocketris to test this. But you can also just take along your M3 for vacation. So it actually does fit into your pocket. It's fairly small. I have it wired up here right now, so I don't want to disconnect it. I'm going to do that at the end of my presentation. Now, everything I do, I'm an academic, so I never quite figured out the business model of making money. So everything is open source. So from the schematics to the PCB layouts, all the software is all at this GitHub link here. I'm going to post the slides later in Discord for Tandy Assembly, so you can then also look at the slides later. I did want to talk about the ESP. Again, I'm a big fan of the ESP. It's a low-cost microcontroller that includes Wi-Fi and Bluetooth, and it's just kind of amazing what they squeeze into this little tiny thing. The reason why I'm using the ESP W Rover B, which I've not used for Tris.io, is because this one here has also some what is called PS RAM, pseudo-static RAM of 8 megabytes. And I need that because of everything that's happening on this emulation. So Tris.io is embedded, and the VGA emulation. So it's just, the dev board I was using for Tris.io just doesn't work here. But it has quite a few things. It has 16 GPIO pins, which is not a whole lot. And I also had to work around that a little bit. I'll explain in a second. But it has a lot of peripherals, SPI, I2C, everything that you may want to need. And I pretty much use everything ESP has. So I'm also using the analog to digital converter to sample the cassette interface. So I'm really making good use of that ESP. Price point, $2.80. I don't think you can really beat that, considering what you get for that price. I want to just do a quick tour through the PCB here. So here's a little bit bigger. So that's the new version 2.3. I had the GitHub link open for quite some time, even before I officially went public. And there were already people ordering PCBs before I even was comfortable on. There was no documentation, but so there are some people who have the ESP in the center of the board here. And then later we decided to follow the ESP design guidelines and also move the ESP to the side and have a cutout here to have a better Wi-Fi signal. But that's the latest and greatest here. Also, as I mentioned earlier, with the 50-pin edge connector down here. So the first thing is here's the top view of the PCB. There's the VGA adapter where you can connect your VGA monitor. to save memory, and again, when you do embedded programming, you have to always be very mindful about memory. And while the library that I'm using here to create the VGA signal can support 8-bit color depth, that would take up a lot of RAM. And I decided to only use black and white for color depth, which then saves some memory on the ESP. But since I wanted to emulate the 3 colors, green, amber, and white, that the old TRS-80 supported, what we ended up doing is we used an MCP 4361, which is this little tiny thing here, which is basically a digital potentiometer. And again, the signal coming out of the ESP is just black and white, so either it's off or on a pixel. But then we use the digital potentiometer to then create these 3 different colors. And I'm using the RGB values that George Philip provided to me from his TRS-80 GP emulator. Here is the PS2 connector. Again, it's a top view, so you cannot like see the front view, but here's where you connect the PS2 keyboard. Then here is the audio jack, the 3.5 millimeters audio jack. And again, this is used for both creating game sounds, and you can also then use it for cassette input. And I hope that I can demo that a little bit later than during the demo. One big update of the 2.3 version of Pocket Tris is that we also added a micro SD card. As a matter of fact, then I gave also Tris.io a facelift and an update. So all my projects now support micro SD cards. Tris.io for the Model 1, for the Model 3, and also here for Pocket Tris, we added a micro SD card. So it's on the back side. You can just see this actually has a micro SD card plugged in. And you may remember from my earlier work, Tris.io also includes FRET functionality. So, but I've been using SMB share so far. So you had to host the FRET.ROM and the hard disk images on an SMB share. Now, that still is supported, of course. So the ESP has Wi-Fi, so you can still do the same thing as before. But now, if you wish, you can also then just put in those images on a micro SD card, plug it in. And if you have an SD card plugged in, then it has precedence over the SMB share. So in case you configured both. So that's one big update for Pocket Tris, but as I said, we also I gave Tris.io an update here. And then last but not least, and here's maybe the reason why hardware emulation goes beyond on what you have if you just do software emulation, what you typically run on your Windows or MacBooks. There is a 50-pin connector down here where you can connect peripherals. And if you're on Discord, you know that Matt, who will then give the next part of the presentation, managed to actually connect an old external hard disk to Pocket Tris. And that was like super cool. I mean, there was some debugging, and I don't want to go into that. You can read up on Matt's summaries. But that was kind of like the gist of why I even wanted to do Pocket Tris in the first place. So to be able to connect vintage hardware peripherals, just kind of flipping it around. FRET is a modern card that plugs into the old computer, but Pocket Tris allows you the flip side. So you have like a modern emulation of Tris 80, but then you can plug in vintage peripherals. Now, I had to include 2 port expanders here. So I'm using 2 SPI-based port expanders because you saw on an earlier slide, there are only 16 pins, 16 GPIO pins. And I already need a lot for the buttons, for the audio jack here, PS2, VGA. So there was just no way how I could control the 25 pins of the expansion interface. So I'm using these 2 port expanders driven by SPI, but you can imagine it's not the fastest. It was also the issue that then Matt ran into when he connected a vintage hard disk. So basically, I simulate the whole I/O timings with assert, I/O request, assert, read and write, put the address on the address bus. I simulate that by pushing out then these instructions to the port expanders here. Last but not least, then there's a little connector here, and you need an external programming interface, so an FTDI adapter that connects to your USB. If you wanted to update the firmware, that is what you would need. I know there are some people who are purchasing, who are selling Pocket Twist boards. I guess they already come pre-flashed. But if you wanted to, then as I'm adding new features, you would also need to get this programming interface. Okay, demo time. So what I am doing, since I'm remote here, I have connected my Pocket Twist board to the VGA, to a VGA capture card. So basically what you see here on my screen, that I think gives you the clearest picture. So instead of holding a camera to a VGA display, I thought it's better if I use this capture card here. So let me just switch to keyboards real quick. I've been talking here nonstop. I hope you guys can still hear me. I mean, I wish I had some feedback that you guys can actually hear and see what I'm doing here. I think I have still Discord open, so maybe someone can just quickly type, yeah, in Discord or something. Okay, yeah, thank you, Sasha. So I'm going to just do a hard reboot of the ESP. So I'm already here in the Fret menu, but let me just do a hard reboot because I want to do a quick shout out to Kyle Watson, who, oh, come on, to Kyle Watson. You can just saw like this little splash screen show up, and Kyle created that. So Kyle, if you hear this, thank you so much. I really love your flash screen. Now, the Model 3 ROM that I'm using here already has the Fret ROM C patch integrated, which means if you have this SD card pushed in, mounted, or if you have the SMB share mounted, then you will get to the familiar Fret menu here. So I can now select the images. I can go into new DOS here. I can just do different stuff. I can, let me just also turn on the sound here. So so the ESP is connected to my Wi-Fi network here, so I can also then launch the Retro Store. If you remember the very first Tandy assembly, the very first thing that Sasha and I presented was the Retro Store. Yeah. Yes. Oh, crap. Yeah, right, because I forgot to, sorry. Okay. Where's, wow. I just, okay. I just have something really weird. Let me go back to, oh, sorry. Stop share. I think I just killed my Zoom here. Yeah, that's the slide. I want to switch to the capture window. Wow, I cannot even get to the menu back here of Zoom. Wow, I need to restart Zoom here. I have no idea what's happening. I'm going to force kill my Jesus. Cannot do anything here anymore. I cannot hear what. So I'm totally frozen with my laptop here right now. I think I was doing something not so good. Yeah, that's the beauty of demos. Let me just unplug this here. Yeah, okay. I think I managed to unfreeze. I think the capture card that I use here is interfering with Zoom. That is Wow. Okay, this is not good. Let's reboot, see if that works. Let me screen share the capture card. So this is the capture card, but now I don't see, that's what I was afraid of. Can you see the screen? Oh, thank God. Okay, demo just started working again. So let me start it from the top. So let me reboot the ESP so you can see Kyle Watson's nice artwork with the splash screen here. Since you couldn't see that, isn't that nice? Thanks, Kyle. So again, I'm using the ROM 3, the Model 3 ROM with the fret patch. So that's why, since I have an SD card mounted, I get the fret menu, and I'm launching new DOS. You remember I came first to Tandy Assembly with Sasha to talk about the Retro Store, which is a hosted web service with vintage applications. You can download them from the Android emulator, but we also wrote a native client. So what I'm doing now is I'm launching the Retro Store client that runs now under Pocket Tris, and I can browse now. It uses Pete's Trisnic to connect to the Retro Store backend to get a listing of all the applications that we have hosted there. And let me just launch Cosmic Fighter here, because it has game sound. So if I hit now enter again. So that's the game sound. When you hit the F3 key, you come into a Pocket Tris configuration here. So you can do a few different things. You can ask the status here, so you can see that that I'm currently have an SD card mounted, but SMB is not configured, but I am connected to Wi-Fi. I can go into configuration here. I can do different things. I can select the time zone, so it automatically syncs the time. But what I want to show here is I can change then the screen color. So going to amber, and I would now be then in amber here. I think green comes across a little bit nicer. So let me go back to, let me do white here just to show, well, it's more bluish, I guess. I don't know. That's the capture card. Let me go back to green. I think it's my personal color. Okay. So let me reboot Pocket Tris, but hold down the break key, which gets me to the cast prompt. And I'm going to do L for low speed, 500 baud. And I'm going to now attach the audio cable here into my laptop. And then I'm going to type system. Sorry. So now it is waiting for an audio signal. So what I'm going to do now is from my other laptop, I'm going to hit the play button. And this is a little bit of hit and miss, just like with the old machine. And you can see in the top right, the flashing asterisks. And you also have to wiggle with the volume a little bit. And I hope I don't have any emails coming in now while I'm doing the demo that would disrupt the audio signal coming out of the laptop. This loads for 90 seconds. So let me see if I can, if it runs through here. So anyone know a joke? Germans don't know any jokes, sorry. Germans are not funny. So it flashes, no corruption, so looking good. So this is now, I play the WAV file that Pete posted on his breakdown website. And I'm playing the audio signal into Pocketris, and then the ESP is basically using the analog to digital to digitize that and feeding it into then the emulation, and then the ROM is interpreting this now as ones and zeros, and that's why you see in the top right corner those flashing asterisks. And I really don't know what to say anymore. I wish the 90 seconds are up. Okay, I actually can see, okay, a few more seconds to go. Still no corruption, so looking good. And, okay, let's see. Ta-da. So I just loaded Pete's breakdown from the cassette interface. And I'm horrible at playing this game, so I won't even try. Anyways, so let me go back to, that's the demo. Let me go back to my slides, and then I'm going to hand over to Matt so that he has enough time. You should be able to see my slides again. Okay. Yeah, there's quick things here, just some historical things. I dug out some old pictures. So obviously you start with breadboarding. So that's, you can see that I actually started with the ESP dev module that I'm also using for Tris.io. And that worked, but I was not able to integrate Tris.io because I just needed more memory. That is when I switched over to the WRover B module I mentioned earlier. But that's basically the first time I got this thing to work. You can see the VGA adapter, PS2 connector. Here's the audio connector up here. Down here is the 50-pin connector. Some historical moments. Here's when you can see, here's this breadboard I just had showed earlier. Here's a Tris.io card, and you can see the ribbon cable where I connect Tris.io to Pocketris. And here's a VGA monitor where you can see for the first time I managed to boot Fred off the external Tris.io card here, running Pocketris on this breadboard here. Of course, there were some interesting snafus in designing the PCB. So we had the wrong footprint. So the VGA adapter didn't quite fit the footprint here. So I had to do some fancy soldering to, and I'm really proud of connecting like 9 pins, even though the spacing didn't work out. But at least we had some evidence that it worked. And then, you know, we fixed the footprints. For the sake of time, I will just mention that, you know, I mentioned this slide, Frankenstein's monster. I'm an open source guy, so I don't have the ambition to start everything from scratch myself. So I'm happy with all the excellent work that smart people have done out there, and I can just add my little delta on top of it. So here are all the libraries that are in Pocketris, and I guess that's why I call it Frankenstein's monster, because I'm just putting everything together just to make this work here. And just maybe to mention a few of them. So of course the Espressif from the ESP, they have an excellent development environment, super capable and lots of features. Here is the VGA library for the ESP. That is a developer from Rome. Also a super smart guy who just did some amazing work on the ESP. I'm using a dedicated Z80 emulation library that was easier to integrate on the ESP. But then I've also literally butchered SDL TRS to pull out a few things. So for example, this cassette interface. So SDL TRS can also read WAV files from a file. So what I've done is I've taken that code and I've ripped out the fopen from a WAV file and replaced it with the analog to digital converter on the ESP. The whole of Tris.io is a sub-project of Pocketris. So basically it's like a Git submodule. There is the SMB is a separate library that I pull in. There's an integrated web server, Mongoose, an embedded web server. And in the early days, Fred Verkoven, the author, creator of Fred, also gave me his source code that is also part of Tris.io. So I have a walkthrough here of the source code, but since I don't want to take away time from Matt, I know he has some amazing stuff to present. I'm going to paste the PDF in a bit in the Discord channel. And these are all links to the GitHub repository. So you can actually see, for example, your cassette input. You can just click on that, and then it takes you to the GitHub source line where this is actually happening in Pocketress, if you're interested to look at the source code here. And yeah, last slide. Let me just say here, pull requests always welcome. Again, I'm an open source guy. The one thing I really that I appreciate what Matt did is here to attach an external hard disk, and I believe in the exhibition he's actually showing that. So make sure if you are in Springfield to take a look at that. This is just kick-ass, Matt. Kudos to your work there. Okay. I would suggest I'm going to hand over to Matt right away, and then we can do a combined Q&A at the end. And I don't know, Pete, if I can also listen to Matt's presentation here, or if I should switch back to the YouTube thing. What do you suggest? Can I listen into Matt's presentation, or should I switch to the live? Yeah. Audio is not great. You know what? I'm gonna mute myself here, and I will stay on this Zoom link, but I'm gonna also then go on the YouTube link. Matt, it's all yours. Thanks.
It's working now? It's working now. All right, well, very good. So, well, I don't know how to get rid of that little timeout. What's that? No.
Yeah, over to the
To the left? Thanks. You can tell how much I do presentations. So, actually, I hate Microsoft Office. So anyway, I'm going to present a kind of a similar project, but FPGA-based emulator, similar to Pocket TRS, called Scope 80. And if you haven't seen any of my posts on Discord, you'll soon learn why it's called Scope 80. A good subtitle for this presentation is A Tale of Many Tangents and Missteps.
You guys have mentioned the Discord channel.
Yeah.
Can you tell us what channel that is?
It's a Tandy channel. Pete, I think, is the administrator for it.
Yeah, I'll send you.
Yeah.
Anybody who wants to invite, it's a closed Discord, but we welcome everybody.
Mm-hmm. Yeah, so I've been posting my progress on the Discord channel, Tandy channel Discord. So if you haven't seen it, then like I said, in a few minutes you'll know why it's called Scope 80. The appropriate subtitle is A Tale of Many Tangents and Missteps, because anybody who's developed an emulator quickly realizes it's not about the things that work, it's about the things that don't work. You build it and you expect everything to work, and then you quickly find the things either don't work or they don't work the way that you expect them to work, and they just lead to interesting journeys as to why. And then you fix them and then you go on. So anyway, does the world need yet another TRS-80 emulator? And the answer is no. So why? Well, one day, I think it was, is it Paul Burrell? Paul Burrell? Yeah, so Paul posted one day on the Discord channel, just, this post about a Z80 compatible core called the Y80. And, an FPGA-based emulator or an emulator of any type was just nowhere on my radar, but I saw it, and I just happened to be working on a FPGA design at work, and I thought, that's kind of interesting. TRS-80 is pretty simple, the processor, RAM, ROM, whatever. Maybe I'll take a look at it. So I just have to work on design. It's pretty simple, and So, I had the core. The FPGA design environment provides memory blocks, ROM, RAM. Keyboard I could emulate with a UART, it's pretty straightforward. But the display was really the problematic part. My board didn't have a display, no convenient way to connect the display, so what to do? So I decided was to rely on an old trick of using an oscilloscope as a CRT display. And so here we have it. So I implemented it, and we have our TRS-80. So it's just a little bit of information about how that works. So, CRT is a raster display, and the oscilloscope itself naturally provides a horizontal raster. But what we really need is a vertical raster. So what you do is you just connect the row counter, which is counting through the rows of the display, to a DAC, which essentially sweeps you down through the display. And analog oscilloscopes anyway have a not very well-known feature of a blanking input on the back. They usually have a blanking input, which really is what allows this to work. So this isn't really to scale, but I wanted to show. So what we do is we output basically a horizontal sync pulse, which synchronizes the scope display. So kind of to scale, this is what the horizontal sync looks like with respect to the vertical sweep. And so it sweeps across the display, and then we just feed the pixel information. We get the display like you saw it. And play here today, so or this weekend, so stop by and see it. So this just gives you an idea of what it looks like with no with no actual pixel data. It just gives you a white display, and so you can see it's white. And you see there's a few lines across the scope. Those are actually due to DAC imperfections. They're not. I actually don't think they're problems with the DAC. They're just a combined interaction of the DAC and the circuit. You see a little bit of retrace artifacts in the upper left-hand corner, but for the most part, I mean, it provides a pretty usable display, and for lack of anything better, that's what I had. So that's great, but you saw I ran like a simple basic program, but what if you want to run something else? So the FPGA has a kind of convenient feature where RAMs can be initialized. So what I did is I preloaded the RAM with one of our favorite programs, Galaxy Invasion, and it worked. So I thought that's pretty interesting, pretty encouraging. But at this point, I thought, well, okay, I was looking for something to demo, something not present, but to demo. And I thought, well, if I'm going to demo it, I need to get it off of my work FPGA board. So I started looking for some kind of evaluation module, and I came up with this one here, which is called a CMOD A7. It's from a company called Digilent, which makes a lot of FPGA eval boards and demo boards, things like that. And it's kind of hobby class stuff. It's fairly inexpensive. It's pretty easy to use. It just happened to be the same FPGA that I had been using, which was rather convenient. I wasn't really looking for that, but it happened to be the same Xilinx FPGA that I was using. It's got some nice features. It has the USB for power, for JTAG for programming, and it provides a virtual COM port, so you get a UART through your PC. It has this thing called a PMOD connector, which is kind of a standard expansion connector that Digilent, it's kind of a pseudo de facto standard. And they have a lot of different PMODs. You can get DACs and PS2 connectors and A to Ds and all kinds of Wi-Fi boards, all kinds of things. So that was convenient because I needed a DAC for my vertical, the vertical trace on my oscilloscope. So it looked pretty good. And it had another interesting feature is it had static RAM rather than SD RAM. A lot of the FPGA boards have SD RAM on them, and this had static, which is just a lot more convenient, and especially for this class of a project. So the first rule of design is you can never have too many LEDs. And so, of course, one of the things I was interested in is how many LEDs do they have, and it's only 2. But for a little tiny module, okay, 2 is acceptable. It has an RGB LED. But one thing that was really interesting is it's in a 48-pin DIP type package. And so one row of the 48-pin DIP is 24 signals, 3 plus ground, and the Model 3, Model 4 expander is basically 23, 24 signals. And I saw that and I thought, could I just plug that into, one row of a ribbon cable connector and connect this to an external device like a Fred? So I thought, well, give it a try. And so I made this adapter, and you can see the ribbon cable is a little bit special because, like I said, it's 24 pins versus 25, and ground comes over on it as well. So there's a couple of signals on that end of the cable that aren't used, so it made it really convenient. So, of course, will it work? Well, yeah, of course it worked. It's a TRS-80 emulator. It should work, right? So, once you have the Fred working, then you have all kinds of programs. So we went from, being able to run one program that was preloaded into the FPGA RAM to running pretty much anything. So I thought, okay, that's pretty cool. But anything that connects to a Fred has to run Trisvid. So Trisvid is the killer application for the TRS-80 and the Fred. And I'm like, at this point, everything's been success. So, will it work? It's inconceivable that it wouldn't work, but it didn't work. So what's wrong with Trisvid? Well, nothing's wrong with Trisvid. So, by definition, anything that works on a real machine but doesn't work on an emulator is the emulator's fault. So let me rephrase that. What's wrong with my emulator? Well, this is one of those tangents you go down. So what was wrong with it? So I did this investigation and kind of figured it out. And what it turned out was that Trisvid requires a special Fred firmware that George developed. And in general, he made the firmware, the I/O faster. But in doing so, he reordered some of the instructions, and he actually made it operate slower in what I call recovery time. So his access time was quicker, but the time between accesses, the time required between accesses was longer. And the core that I was using wasn't psycho-accurate. So it was actually running faster than a real TRS-80. And in particular, in this type of I/O loop, it was quite a bit faster. So what I found was that the kernel of the data transfer from the Fred is an INIR instruction, which is a block move input instruction, which ran, like I said, particularly fast in the emulator. So what I did is actually hacked, I think, the Fred loader, Trisvid, and the LDOS hard disk driver, and I replaced all the INIRs with a loop, which is INI and jump back to the INI. So those two instructions are effectively the same as the INIR, but they run slower because it forced the Z80 emulator to reload the opcodes. See, with the emulator, with the Z80 core, it actually wasn't reloading the INIR opcode like a real Z80 would, and that's why it ran so much faster. At that point, it worked, but I realized, I could do it to these few programs, but if I want this thing to really run any software, I accurate. So I switched cores and I went to something called a T80 core, and that's psycho-accurate. So this shows you why the Fred firmware didn't work. So in George's 3.0 firmware on the left, you can see at the beginning, at the top of the that listing is actually where it does the I/O, and at the bottom where it does that wait is where it recovers for the next transaction. And because he had it at the bottom of that construct, it was too slow. So by just moving that up, then it actually worked, and then I was able to go back to the original software. I didn't need my hack software that had those, the INI and the jump instruction. I mentioned the LEDs. Those are important. So how did I use them? So the second rule of design actually is you always have to have a blinking LED, because nothing impresses people more than a blinking LED. They don't know anything about what you're doing, but they're impressed by a blinking LED. So you have to have a blinking LED, and I call that the heartbeat LED. And generally, all of my designs will have a heartbeat LED, and I usually use a solid. If it stops blinking, that's bad. That's usually some kind of a fault condition. So it has a heartbeat, and then I use the second LED for what's called the CPU fast. So in a model 4, it runs at 2 or 4 megahertz, and they call the signal that controls that CPU fast, or at least the bit that controls it CPU fast. So I use one of the LEDs to indicate whether I'm running at 2 or 4 megahertz. Then on the external expansion connector, there are 3 signals that are input from the outside world. One's called external IO select, one's called external IO wait, and one's called external IO interrupt. So I connected those to the RGB LED, and it's kind of interesting. So when you're doing external accesses, you typically get a little bit of a light show on that LED. And then, of course, you have to have a Z80 reset. So use one of the buttons for the reset, and the other button is turbo. So arbitrarily, it currently makes it run. So if you press the turbo button, you got some high speed. And I don't know what the practical maximum speed is for the FPGA emulator. I just picked 48 megahertz somewhat arbitrarily. But certainly doesn't have any trouble running at 48 megahertz. So, since then, it's matured a bit. I've created 3 versions, Model 1, Model 3, and Model 4, and variations within there. So when I say variations, I mean ones that run from internal FPGA RAM, ones that run from the external RAM, ones that use an oscilloscope for a display, ones that use VGA for display, and so on. I've added cassette output for sound, primarily. I've added high-res graphics. So for the Model 1, I'm emulating a low electronics 18. I didn't even know what that was until maybe a month ago. Never had it from a Model 1. And for the Model 3, Model 4, I emulated micrographics. Added the VGA output, as I mentioned. Use external SRAM on the FPGA module for main memory. And I added Orchestra 90. So the Orchestra 90 is a bit interesting. And since this is a tech talk, I thought I might talk actually a little bit technical. So one of the problems we have on the FPGA is it doesn't have any DACs. And the Orchestra 90 is essentially a stereo 8-bit DAC. So how do you implement Orchestra 90 on an FPGA? So you typically use some kind of a 1-bit sound format. And there are a couple of popular ones. One is called pulse width modulation. So in pulse width modulation, so the idea is with these formats, so you can use a digital output to essentially emulate a 1-bit DAC. So then you need a format that's compatible with 1-bit DAC. So pulse width modulation is one, and that's actually what Trisvid uses for its sound. But a more convenient one is actually pulse density modulation, and that's the one I implemented. So most people here probably remember CD players and 1-bit DACs and CD players. This is the technique that they use. It's a pulse density modulation, and it's also called sigma delta modulation or noise shaping. And so in pulse width modulation, you vary the duty cycle to represent the amplitude of the signal. So if you have a wide duty cycle, then it's a large amplitude signal. If you have a low duty cycle, it's a small amplitude signal. With pulse density modulation, you vary the density of the ones to the zero. So if you have a high density of ones, you have a large amplitude signal, and if you have a low density of ones, it's a low amplitude signal. How do you generate that? Well, it's really quite simple. You do it with an accumulator, and you feed the input signal, and then you just feed the output, the accumulated value back, and you take the carry as your output. So every time you get a carry, you get a 1, and every time you don't get a carry, you get a 0. And I'll demo that. I actually have the Orchestra 90 demonstration, so you'll get to hear that. So I'm going to give you an idea of how much of the FPGA this is using. So I have an example where we have the external RAM, and we have an example with the internal RAM. And other than the RAM utilization, they're going to be the same. So the lookup tables are essentially logic. Lots are lookup tables. So in an FPGA, all the logic is implemented with lookup tables. So you can see to implement, implement a pretty much a full TRS-80, we're using 9% of the logic, which is rather minimal. We're using 2% of the flip-flops. The RAM we're using a fair amount. So we're using half of the RAM if it's in a 64K internal, and we're using about 20% of the RAM if we use the external RAM for the main memory. BuffGs are basically buffers. They're not really that important. That's a fairly, I don't know how many of them there are on the chip, but there's not a whole lot. So 13%, it's like, maybe, a handful of a small number. The MCM are actually your clock generators. There's 5 of them on the chip, so I'm using 1. So that's what I said. So 20% might sound like a lot, but you got to use 1 on your design. So I'm using 20%. So a lot of room for expansion. So what are the next steps? So what I plan to do is to make a baseboard that will hold the that module that I talked about, and that will give you the connectors that you're typically used to. I'll have the VGA connector, I'll have the 50-pin expansion connector, have a cassette input and output, or cassette connector for input and output. I'd like to do floppy. Peter Bartlett was, oops, is he over there? Yeah, he was kind enough to actually release his Verilog floppy design. So I plan to try to integrate that. The TRS-80 UART, and then include the 5.0 level shifter so that we can connect to, to real devices without having to resort to anything special, and then bring it here next year. So I think that is, oh, one more slide. I forgot. Yeah, so I wanted to just kind of compare the software and hardware emulation. So Arno presented the Pocket TRS, which is the software version. And as he mentioned, you get a tremendous level of integration with, with that SOC for an amazing low price. So you get a lot of peripherals. You get Wi-Fi, Ethernet, USB, SD, everything. You get a lot of networking, TCP/IP, SMB, and so on. One of the downsides, though, is it's not cycle accurate. So it doesn't emulate, real machine quite as well as you would like it to. But you can connect, real peripherals, a real hard disk, a Fred, and so on. And as I mentioned, it's extremely low cost. The hardware, probably the main feature of the hardware is you can come really as close to emulating the true hardware as you want. You might say, well, why wouldn't you want to emulate it exactly? Well, it's not that you don't want to, but an FPGA technology is different than the LSI, MSI technology of the past, and you just don't design the same way. So for example, for the display, the FPGA actually implements dual port memory. So for the display, I use dual port memory rather than muxing a single port memory for both video and CPU access. So that gives you a little bit of difference. If that's really important to you, you can go to the trouble and you can do it all with single port memory and make it even more accurate. But basically, when you design, you take a few shortcuts, and then if the shortcuts cause you problems, then you go into more detail in that section. You can connect real hard disk and so on. Probably the biggest negative, it's higher costs. And the FPGA module is about $80 compared to $3 for an MCU system on chip. So that is the last slide. So after that, I do have a demo. And for that, I will have to come over to this side. All right. So hopefully nothing breaks in the meantime. All right. So I mentioned about how we can, let me check the time first too. Okay, good time. So I mentioned about how we can preload a program. Well, that only occurs when you boot the FPGA. So I'm going to boot the FPGA to make sure that we got a fresh copy. It's RAM based, so it loads really quickly. And then I'm going to hold down the break key. Can't see. Let's see. There we go. Okay. System. Oops. Can't type. There we go. So, all right. So that was Galaxy Invasion was preloaded into the FPGA RAM. So I just boot up and then I just type system/34304 and we're running Galaxy Invasion. Okay, so now I'm going to go ahead and boot the Fred. So this is running the Fred auto boot ROM as well, just like Arno's Pocket TRS. So it boots the Fred, and then we can have a lot of different things to choose from. So we can run LDOS and there's another demo program. Let's see. Hopefully this works. You recognize that voice? George, yes. Yeah, so some time ago, I think somebody posted on Discord again, I think some type of a program that maybe used a voice synthesizer or something. Welcome. And so George posted, well, for people that don't have the fancy hardware, here's your thing. So that's George. And more George. So here's one that Tim will appreciate, I think. We'll see. I'm looking for, oops, wrong one. No? I thought Flash, yeah. Pittsburgh, yes. Yeah. So I'm originally from Pittsburgh. Tim lives, you originally from Pittsburgh? Okay. So he lives in Pittsburgh, so. Yeah, so Trisfit, or Flashdance happened to be filmed just off the University of Pittsburgh campus when I was going to school there. So they took my parking space when this was being filmed. So, yeah. Yeah, so anyway, I actually have quite a few videos. I digitized a bunch, converted a bunch more for the show. I actually have the full movie Grease that we're playing back here. So that's another one. Let's see. We're running out of time.
George's bean packing demos run out? Like bouncing ball?
They won't. So actually, that is one I may have. Let's see. No, let me try ball.
Yeah, ball.
Well, I had a converted one. Okay. So it doesn't really work on it. Right. Yeah, I'd say I don't have video weights. I mentioned how I use a dual port RAM, so I don't have the video, and this relies on the video weights. So if that was important to you, then you would go in and emulate all that stuff more faithfully.
Yes, the Model 1 takes hardware.
Yeah, so this is a Model 3. It should work, except I don't implement the weight states. And that's, so what he does is he synchronizes initially to the display, and then he synchronizes the weight states. So that does not work. But I'm glad you brought that up, actually. Let's see, what was one of the ones I was going to? So this is an interesting one here that doesn't work. So I said, these things lead you kind of down these tangents. So I thought, ORC 90, it should work. Oops. Oh. But it reboots. Why didn't that work? So I disassembled the program. I'm debugging in TRS-80 GP. You know why it doesn't work? Because you have to type it in uppercase. Can you believe that? If you type it in lowercase, it reboots. And I disassembled it to figure that out. But sure enough. All right, so let's see. Actually, I do want to play some other videos. I'm probably running out of time. Just to compare them, but all right, I'll try it. So this is an interesting one too, because the keyboard doesn't work quite right on this one here. So, which I won't go into, but it's a little painful to type because it doesn't, the keyboard doesn't work quite right. Oops.
Is it doing some sort of weird poll?
Yeah, what happens is because I emulate the keyboard with the UART, I can't control how long you press it. So I'm just emulating a certain keyboard. It's not long enough for it. So I have to actually press and hold, and when it repeats, then it picks it up. So hopefully this will play. Oh yeah. So that's Orchestra 90, and this, I had never heard an Orchestra 90 before, so I have really had no idea if this is what it's supposed to sound like or not. But, yeah. So here's one more. Let me try, let me see, G. I forget the name of the file now. I'll try, I guess. Oh, it is. I got it right. Good. It'll play. So this is Uptown Girl by Billy Joel. So the reason those are kind of significant are because I also have those on Trisvid.
Oh my Lord.
So you can compare.
That's amazing.
So there's that, and then yeah, I said, so I also have Uptown Girl, the video. Starts out a little slow. So, but yeah, you can stop by my table and see it. So everything so far has been Model 3. Oh, I forgot. So you can't stop Tristan while it's playing. I should have stopped the video before I hit reset. But we can boot. This will be a Model 4 LS-DOS, and it has high resolution. So. And I guess I probably haven't emulated the screen, the XOR display. It's actually XOR. I should hit clear screen first, but you can see it's blending the text screen with the graphics screen. I think Space Invaders on there. Okay, Space Invaders is on there. Okay, so Space Invaders is a really kind of interesting hack, but it's a high resolution game that runs on the Model 4. I mean, it's actually the arcade game that somebody hacked to run on the Model 4 that uses a high resolution screen, which is really a pretty interesting piece of work in itself. If you've never looked at that project, it's certainly worthwhile. HRG Test is a program that tests the high resolution graphics. I don't know if anyone's ever run that program. If you have run it, I'm not sure if you've ever made it to the end, but here's Turbo. If you want to see it go a little faster. Yeah, so there's regular speed and there's Turbo. So it's.
Yeah, it definitely doesn't run like that on a real time.
Yeah. Yeah, I'd never seen the end of HRG Test until I ran it in Turbo mode. So. But anyway, that's like I said, I have the scope version on display, I have the VGA version on display, and I have a Pocket TRS version on display. So that's it. Didn't run too far over.
Oh, test 1, 2, 3. Test. Does it work? Can you hear me? Test. You can hear me? Yay. I can hear you very well. Thanks for the setup. Excellent talk so far. Let's see if I can get my presentation up. Hey, Pete, can you hear me? Or anybody there? Can you let Arno into the meeting as well? I think someone needs to click a button to admit him. Awesome, thanks.
Hey, Pete, can you hear me? Pete?
I can hear you, Arno.
Okay, I was muted. Pete, can you hear me? Pete? Later on, I'm going to log on from a different laptop, so then you would also have to admit me to the Zoom session again, just to let you know. Later on during the demo, I'm going to log on from a different laptop into the same Zoom session, so you would have to admit me. I will let you know. So I'm gonna do a little demo later on, but I'm gonna do it from a different laptop. So, but I will join the Zoom session. But I've noticed that you have the waiting room enabled, so you would have to also then let me in. Yes. I'll let you know. I'll let you know when the time comes.
We'll transition at some point.
Yeah. I'm just crashing the party, you know.
You stole a slide earlier. I saw that.
Well, I saw the demo slide, so I thought, why not just take it?
Thank you. Should be.
Our next presentation is starting, so please take a seat. All right, great, thank you. All right, yeah, welcome. Welcome to this tech talk. Bit of a different one, potentially. Let's see, thanks, Pete, by the way, for and everybody there setting up this link. It's great that we can actually present here while not being actually live there. So thanks for all of that. I know the technical hurdles that go into getting that to work. So this talk is about TRS X-ray. What is TRS X-ray? Like in one sentence, if I had to describe it, it's an extendable, system-agnostic, web-based debugger front end for the TRS-80. What does that mean? Like, there's a lot of words, but I'll go into some of the details now on the next slides, and I'll spend a lot of time in a demo because that's probably what most people think is probably like the most interesting part of this. Super quickly, who am I? Why should you listen to me? Well, that's a good question. I don't know, but I've always been like, curious about combining old tech with new tech, figuring out how to use new technologies to make these like old systems come to life in one way or another, or to help people understand them better, people including myself. Basically been coding my whole life. You probably know Arno's Android emulator that I worked quite a bit on as well back then. Created retrostore.org, which we presented a few years ago, and also contributed a little bit to Arno's toy projects here as well. So let's see, like quick overview here. Well, at the beginning, I just want to explain to you why am I trying? Why did I do what I did here? Then the what and how, just giving you a little bit of an overview, and then really focus on the demo because I think that's just going to be like the most interesting part. And then, as you can see, Arno here is also on the call still. That's not a coincidence. So we have like one more thing at the end. So Apple, please don't at the end here. Right? Why did we create this thing? So it all started Cockatrice. I think at someday I remember Arno gave me one, and he was asking me like, hey, could you help me with something? I wanna make this thing print, but for real, could you create like a website that is embedded onto Cockatrice that could just print out like a line printer would, and then we could print it for real, PDF or something. So I thought, well, sure, that's easy enough. That should not be a big deal. That should be pretty easy. I didn't have any of those. I moved from Germany at some point, 9 years ago, and I didn't bring any of my old hardware with me. So I had nowhere to connect this to. If you connect to CRT and a big keyboard, then it's not really very pocket, is it? So I thought, well, in order to work on this, let me see what could I do. So Cockatrice already has a web server built in, as you heard from Arno earlier. So I thought, well, instead of just getting the bytes over for the printer, let's just get the whole display over to the website, right? This way I could see it. And then likewise, what I could then do, I could then go ahead and get all the keyboard inputs from the website down back to Cockatrice. So this way I can just, use whatever machine I have and use it now, right? And I can actually test this. So that's great. That was working. And by the way, going back one slide here, what you can also still see is that was the early days. I found this early screenshot that I sent to Arno, probably being like, hey, it works. Look at this. So you can see in the URL, it actually still says /printer because I never bothered to change that. But then I thought, okay, so I'm transmitting the bytes for the screen. I'm rendering them on that website. But why stop with the screen, right? TRS-80 memory is not that big. I could just transmit all the memory. To do that, you could then visualize it in a special way. You could
see it. You could have different display options. You could like edit it. And then if you pair that with controls to actually start, stop, pause, whatever you want to do with an emulator, now you have this really, really powerful user interface. And you can basically get this onto the system. And yeah, the registers, please. Give me the registers, what's going on with the device. And for me, honestly, I've only been like dealing with like TRS-80 stuff for like a few years now. For me, this was also a great opportunity to just learn how they work. I learned so much through working on this project to see where's the display, what's going on with the keyboard matrix, like why is the stack pointer moving, where is it moving to? It's a really nice way also to teach people new to this platform to see how TRS-80 works on the inside. So, the what and how. Let's take a look here. So yeah, so proof of concept, that was working on the Pocket Tris at some point, and but it's not a full-fledged debugger. So, at some point, I heard like a voice that sounded very much like Arno's telling me like, hey, you should check out STL TRS. This is like a really powerful debugger. It has a lot of bells and whistles, a lot of features. If you can make your X-ray work on STL TRS, that would be pretty good. And so that's exactly what I did, because it might be a bit small in a bit. I'm not quite sure how the compression will work out, but this is basically what you will see here in a second. On the top left, you have all the registers. And then, you have here, this is like a selection you'll see in a second, where I can select individual bytes and you can actually see their value very, very easily. You can set breakpoints, both memory breakpoints as well as program counter breakpoints. And then you see a disassembly section here as well as like the matrix on the right here, which are the actual bytes of the system. But with that being said, it's demo time. So let's take a look here. I hope you can all see that. Let me just check the live stream as well. Yes, you can. So this is now TRS X-Ray running in the browser. Again, on the left, you can see the registers. You can see everything that I just mentioned. And on the right, you see the memory of the current system. These are all those orange little dots. Orange just means that from the last update to the current updates, these are all the bytes that have changed. So you can very quickly see what is changing from like step to step, and it's really easy to see what's going on. What you can also see on the left, if I zoom in here a little bit, you can see the background. Also, by the way, shout out to Lawrence, who's there in the audience somewhere, for actually providing the disassembler. He has an amazing collection of I'll also like link to later that I basically was able to just get in here. And this is now basically running the disassembler as well as a few other features I'll show in a second. But so with that, if I now make that a little bit smaller here, what you'll also see on the right is the screen. So if I now start this program and I just let it run, you will see, you can see the regular output there on the right. I don't know how well you will see it, but basically on the screen now, this thing is running full throttle, right? And you see a bunch of flashing dots, hopefully, on the screen, as well as you see the registers update, you see the disassembler updating. So all this stuff is like updating in real time. And what's really nice is on the screen, what you see here, I'll try to zoom in a little bit so you can see this a bit better, but there are like a bunch of things jumping around. Let me actually stop it. So now I stopped it, and what you'll see is, again, in orange, you see bytes that have changed since the last update. You see a little yellow dot down here. I hope you can see that one. There's like a little yellow dot here. That's the stack pointer. And then here on the right, this green dot, that's the current program counter. So that's basically where we are. And if I scroll up here, you can actually see it's currently at like 33A8. That's just a random position I stopped it at. You can see the disassembler here as well. It's on 33A8. And when I click on this one here, you actually see it as well. So whenever I click on one of these bytes in this selection, you see the address as well as the value that's currently there. So CB in this case. What I can also do is I can actually, as I mentioned, visualize things differently. So this is now just a grayscale. So basically basically from 0 to like max, I basically just shade the byte in a certain color. So that might help you just see certain patterns. It's just kind of interesting to see. It's kind of like reading the matrix, I guess, just the TRS matrix. And if I click one more, you actually see a different visualization. And this time, all the blue dots are basically instructions that you can jump to. And again, this is powered by Lawrence's really powerful disassembler that basically goes over the whole memory and tells me where instructions are and where just like data or text is, or where there's nothing at all. So that's kind of neat. What I can also add is I can add another little thing here where I can now basically single step through, and what you will see is you see this yellow line, and you can basically see now like where this thing is jumping to. You can kind of see it must be reading something from down here as I'm like progressing. If I let it run, you can actually see it's all over the place. It's kind of cool. You can kind of see like hotspots, and then you can kind of try to figure out what is it doing there. I wonder. It's kind of unclear what's going on, but you can then like dig in and actually see what is really going on. So yeah, that's basically that. Another thing that I find kind of interesting is if I make this a bit smaller now again. So as you can see, it's basically just booted. Let me actually just go in here, say enter, enter. One thing that I found interesting, one thing that I learned, although I don't know why that is, I'm pretty sure everybody here knows why, but like the stack pointer used to be up here somewhere in like the 4,000 area or something. Now it is down basically at the bottom of this range. And so if I actually go all the way down, I don't know if that can be seen, but I can try to like go all the way up to the bottom. You can see the stack pointer just like hovering down there. So all the stack is now at the end of the 64K instead of just somewhere in the middle. So that was a nice thing that was just very quickly visualized by doing this. Another thing that I found pretty early on where I mentioned this to Arne, I'm like, I don't know if there's a bug here or if this is supposed to be this way. But like once I start typing, there are like all these like orange things flashing. I don't know if you can see them on your end, but there's like a lot of stuff flashing. Depending if I hit A, I get this pattern. If I hit 1, I get this pattern. I was like, well, that's kind of odd. And of course, then after looking into it, I realized, well, that's the keyboard matrix. So this is the keyboard matrix being visualized here. And one thing that's interesting here as well is, so if you look, once this is happening, what I can do is I can actually click on one of these bytes, and I can then basically set a breakpoint. So if I set a memory breakpoint there, and then I then hit my key again, now the program stops exactly there. And it's interesting, you can just see the keyboard matrix here visualized on the screen. And I thought that was kind of interesting. That's something, interesting to see and to learn from, I think. So this was like a memory breakpoint that you just saw. So I can basically say, okay, if a certain byte changes, stop right there. Again, the good thing was like DLTRS already has that feature implemented. I just had to hook it up. That was pretty easy. Same thing for the program counter as well. Let's see, what else can we do here? So let me just run this again. Let's go in here and let's just run it. So now it's running full steam again. I also, just to help myself, I actually added this little section here where I can now highlight certain areas in memory. So for example, if I hover over here, I see, oh, that's the video RAM. Okay, that's good to know. If I now change the visualization again to this, what you can maybe see here, if I zoom in a little bit, let me actually zoom out one bit again. This is basically the video RAM right here, and you see like a few little areas here and there being not quite black, and that's of course all the stuff that's currently on the screen. So if I disable this and get this back on, you see like this is what's currently on the screen. And I can also guess, what things might be. So I know, for example, somewhere here, like this is 3C40. If I go in there, if I stop the program right now, and I go onto this byte here, you see it's selected on the left, and you see the value is 43. And 43 I know is a capital C, and that's basically the first C up here on the screen, like the cast C. If I now go in here, and let's say I just change it from 43 to 42, hit enter, I've now changed it in memory. And if I just let the program continue, well, you can see on the screen, it's now a B, right? So I can change every single byte in there at any point in time and make changes, which is also pretty nice, especially for debugging. One more thing that I could show as well. Let me see, have I shown everything? I have a little list here to make sure I'm not forgetting important things. Like for single stepping, for example, there's one program that you will see Arno use in a bit as well that Arno actually created. It's like a little program that can fill the screen with characters. If I stop here, I have like a little routine that basically injects this program into my address 8000 hex. And so what I can do now here is I can actually set a breakpoint to 800C. That's something where I know the program will be later, so I can basically stop it there. At the moment, it's 0 because there's nothing there. I add this breakpoint, and now I let the program run again. And what I'll do now is I'll inject this program. So now I injected it, and I jumped to address 8000. And as you can see probably on the screen in the bottom left here, there's this tiny little sliver of orange. And if I go down here again, you can see it again. So basically here now, that's where the program got inserted. And you see it's all orange because that's the first update that I'm getting that the program is there. So let me go back again so we can actually see the screen again. So what you also see on the screen up here is that there's like one rectangle in the top left corner. And that's basically what Arno's program does. It basically just, it takes that character and it pokes it into the first address of video RAM. Then it increments and adds another one. So if I now go and let the program run until it runs into that program counter again, you see a second one up here. So it basically starts growing, right? Every time an iteration happens, you can see this is growing. And what I can also do though, if you look at the left with a disassembler, we're currently at 800C and there's a relative jump there. And you can see it's either just going to continue or it's going to jump to 8006. And if I now single step, you can see it now jump to 8006. Let me actually make that a little bit bigger as well so we can see that a little bit better. But this is basically, your typical, nothing too special about it, but you get all of this information right in here, which is pretty nice. I can just jump around. Okay, and get back to like a more reasonable. Trying to, the UI is not quite optimized for presentation mode, so I'm jumping back and forth so you can actually see stuff on the screen where it's maybe not as clear. But likewise, one thing that I know about this program is that there is, if I single step now one more time again, like there's this like load instruction here that loads BF, and I know BF is basically, is that character, is that rectangular character. So if I go down here and click on 8007, which is exactly, obviously 1 byte after 8006. So it's this argument here, it's this parameter. And I can see here, it is BF. And if I change this one, for example, to 42, one of my favorite numbers, and I hit enter, and I now let this program continue again, well, what you will see is, this has now changed. So if we look at the disassembler here again, it's no longer BF, it's now saying 42. So that live updated as well, which is nice. But then in the top right on the screen, you'll also see that there's now a B. And if I remove this program counter breakpoint and now just let the program run free, you'll see the whole screen fills now with Bs because I made that change in the code, and now it's all Cs. So yeah, that's basically all working. You do that, and as you can see, that's another nice thing. If you just like you type around, you do certain things, and you just see live on the screen what's happening. I hope that's coming across as well on the presentation. But then I do this, and now I could, for example, run this program. I can see the visualization of like where the program counter is going to. I could stop it at any point in time. I see, for example, with this program now, there's this super hotspot up here. Who knows what's happening there? I haven't looked at that in detail. But yeah, it's really, really nice to be able to visualize what's really going on. And hence the name X-ray. It's kind of like, shining a light on what's happening inside the memory, inside the CPU, to really see what's going on there. Yeah, let's see. Have I done? Let me see. I did the breakpoints. I showed the regions. Yeah, I think that's basically all that I wanted to show here. And again, like huge thanks to Lawrence for his tools that really enabled a lot of like all the disassembly that you see here, the visualization of the code regions and so on. So it's really nice to be able to just share that code and make that work. All right, so that's basically that. So that was the demo. It actually worked. Very quickly, maybe like how this works, because you might be wondering how you would implement something like that. So this is going to be a bit of a simplified model, but if anybody wants to know even more, let me know. But I started with SDLTRS, which, as you know, is a C program. It's a native application. So that's what I started with. But I wanted, this interface to connect somehow to SDLTRS. So how do you do that? First, SDLTRS, of course, it has again, this is a rough model, but it has the emulation state, it has some control features, and to those I basically want to hook up to. And TRS X-Ray obviously runs in a web browser. So what I did is I added a native interface, this red box that you see here. And I also added a web server. So I basically added the same web server that is also in Pocketress, because it's a really small, nimble, geared for embedded systems web server. So it was really no problem to add that to SDLTRS. And this native interface is actually the one that's the important one, because if you have another emulator and you want to integrate with that, looking at you, George and Peter, this interface just needs to be implemented. And, the web server obviously as well, but then the rest of the protocol is basically just working because I'm using WebSockets to communicate between the web browser and the web server to basically communicate updates that are happening on either side here. You might also be wondering, well, why a web interface, right? That seems kind of odd, maybe. But, I don't think it is odd at all, right? It's very easy to extend. You can use it this way. You can use it for any kind of emulator, whether that's a JavaScript-based one, whether that's a native one, or whatever it works in, as long as you can, hook it up somehow through, for example, WebSockets in this case, or directly if it's a JavaScript emulator. It's very easy to do so. It's very easy to create very powerful UIs using like a web browser or a web app. And again, it's also super easy to extend. And again, like with Lawrence's tools that are also all TypeScript based, and he has them all available on GitHub, it was very easy to just plug it in. That took almost no time at all. Most of all, what's nice is that this way you can have one interface that works for all different kind of emulators. And if anybody else wants to create another emulator, they don't necessarily have to think too much about, how do I create the UI now? How do I make it so that it's easy to use? As long as you implement this native interface here, you're good. And you can basically use TRS X-Ray. And again, George and Peter, I think it might be fun to at some point ponder whether like either TRS 80GP or even TRS-JS could potentially hook up to this, because I think it would probably be a fun little project. That's that. Well, yeah, the other part, of course, I mentioned at the beginning, that's where it kind of started. This is also working on Pocketress now as well, with minimal changes really, because Pocketress already comes with the web server. So all I had to do was really implement this native interface, and the rest just works the same essentially. Since there are some differences between certain emulators, right? There are different capabilities. Certain emulators might not allow you to do everything. I also like the interface itself has bits in it where you can tell the front end, hey, I have only that much memory, or I can't really update while I'm running, or I can't do this and that. And that's fine. You just set these bits, and then the front end will do the right thing based on these capability bits that you have told it to. So that was pretty easy. Also, as Arno just mentioned, I'm also just like standing on the shoulder of giants here. Mongoose is the web server that we use in Pocketress, and now also I use for this project and embedded into SDLTRS. It's all open source. SDLTRS, obviously, I basically created a fork. I need to take a look whether it makes sense to actually add it proper at some point, but at the moment I have a fork that has all the changes in it that you just saw. And of course, again, like Lawrence's tools, definitely check out his website. A lot of like super well documented and high quality stuff there. And of course, open web technologies, right? I use TypeScript for most of the code, WebSockets for the communication. So it was a great platform. And then, my code you basically find on GitHub as well. I need to document it a bit better, but it's basically all there. If anybody wants to take a look and see how the sausage is made, so to say. I guess one more thing here, as we just mentioned, like with Pocketress, I guess what's really nice is that it's designed so that you can connect real peripherals like these hard disks and so on, because it has this 50-pin expansion interface. So now that now that TRS X-ray can connect to Pocketress, you can, in theory, now contemplate adding features that actually enable you to debug things on that expansion interface even more, and you can actually debug programs that deal with real hardware, which I think could be really exciting to see. And that's the other thing. I think this is just a start. You can add more features, more more functionality, and more visualizations to this interface now very, very easily, because all the foundation is basically there, and you just have to add new channels and new data, and everything should work. So, but speaking of debugging real hardware, I remember at some point, I was pretty clueless about how this all worked with a real Model 1 or Model 3. And so I remember at some point when this was kind of working, I asked Arno, I was like, well, couldn't we just debug on a real device? And I think he was like, nah, well, how should that work? It doesn't make no sense, right? And I think it was like a day later or two, I don't know exactly. He was like, I think I have an idea. I think we could maybe do this. And maybe we can even get this done for Tandy Assembly 2021. So I was like, okay, tell me more. So with this, I would then transition over to Arno, and he can maybe tell you a little bit about this crazy idea that he had. And hopefully also, if the demo gods are with us, maybe even have a demo in store.
Thanks, Sasha. So welcome back. As Sasha mentioned, we had the idea of running X-ray on a real Model 1. So let me just let that sink in. So what I hope later to show to you is to use a web front end to single step on a real Z80 CPU on a real Model 1. And maybe you can see the dark rings around my eyes, so I didn't get that much sleep last couple of days. And the demo gods really have to prepare a few slides or just to explain more in detail on then what you will screen share. So again, the idea is to show now what Sasha has demonstrated to you on the real Model 1. And I first wanted to show you this little program that Sasha also had during his demo. And it is just a proof of concept, right? And if you know a little bit about Z80, and if you paid attention to Tim's class at the beginning, then that should be a no-brainer here. I wanted to highlight a few things. So here I'm loading HL with 3C00, which is, as you know, the top left corner of the Model 1 video screen. Here in BC, I load the number, the 1024, which is basically the size of the video screen. Then here you load BF into where AH points to, and BF equals 191, and that is the solid block that you will then see on the screen. You increment HL to go to the next memory video location. You decrement BC, and then you check if BC is 0, and if not, you just jump back here to label 1. So I know the Z80 specialist amongst you will say, well, you can shorten this. You can use like the LDIR assembly instruction, but the demo here is the point is to single step on Z80 level, right? So that's why I purposefully made this slightly in a less efficient version, but just to show how this works. I wanted to mention a couple more things in this little program here. So first of all, I wanted to point out that this is like, I'm using my Remarkable here for, first of all, notice the entry address here, 8000. So this program is loaded to 8000 in memory, and there's a reason for that I will explain in a second. The next thing I want to point out is here 800C, which is the address of this jump relative not 0. And that is basically, I'm going to show how to set, I plan to set a breakpoint at that address, meaning that we already had the first iteration of the program. So if everything goes well, then by setting a breakpoint right here at 800C, I should be already seeing the first solid block on the screen. The next thing I want to point out is what also Sasha had in his demo, is this load HL address here. That is, okay, let me just change the pen here. This is like not good. So what I also wanted to highlight here is the address of the load HL instruction. And notice that this BF is actually at address 8007, right? And what he showed you earlier is by using the web interface to write a different value here, he used 42. He basically changed the fill character to fill the screen. Okay, so that's the demo program. Then, how do things usually work on a CPU if you want to do opcode level single step? Well, modern CPUs have a special debug mode where there is an interrupt that gets triggered after each opcode, and then the interrupt will then jump into an ISR, into an interrupt service routine, and that communicates with the debugger. So that is usually how things happen on a modern CPU. Now the Z80, it has a few years on its back, and I can tell you it does not have this single step debug interrupt. So once you start running the machine, it just runs. And so it's not really very friendly when it comes to single stepping on Z80 debug level, Z80 opcode level. So what can you do? Well, idea number one. You could use the non-maskable interrupt, build up little hardware, and then whenever you see the next address fetch for the next opcode fetch, you trigger an NMI and you intercept that, and then you insert your debug stub. That probably is possible. The reason why I did not go this route is here because the NMI is not accessible from the expansion interface of the Model 1. So I would have to screw things open, like open the Model 1, do some hardware mods, and I didn't want to do that. I wanted to do, especially for this first iteration, just have a solution that only works with an unmodified Model 1. And plus, I have to be honest, I'm more on the software side than the hardware side, despite having done Tris.io and Pocket Tris. But okay, so second idea. The Model 1 doesn't have the upper 32 kilobytes. So the Model 1 has only RAM on the lower 32 kilobytes. So the upper 32 kilobytes are empty or void, and you know that you can get an expansion interface, and that actually gives you the upper 32 kilobytes. But what about if we use this to debug on the upper 32 kilobytes? And let me explain you how this works. So here you have all of RAM. So you have from address 0 to address FF. So only the first 32 kilobytes are actually, that is what you have on the M1. The upper 32 kilobytes don't exist on the Model 1, but the expansion interface gives you access to all the 16-bit address lines, and it also gives you access to the 8-bit data bus. So then here's what I did. So here I have a Model 1, a Tris.io for the Model 1. And Tris.io for the Model 1, I added this 32 kilobyte chip. So if you have a Tris.io for Model 1, it has already integrated an SRAM chip for the 32 kilobyte RAM. So step number one, I removed it. So you see it's an empty socket. And then I reprogrammed the GAL on the Tris.io here to then reroute access to the upper 32 kilobytes to the ESP. So basically what happens here now is on the ESP, I have an array I call VRAM, virtual RAM, that is just 32 kilobytes in size. And whenever the Model 1 I should have thought of my little animations here earlier. Whenever the model 1 accesses an address that is greater or equal than hexadecimal 8000, it actually is intercepted by the ESP, and the ESP is then getting this byte from VRAM and sending it back to the model 1. Okay, so basically I've butchered the TRIS-IO card to act as virtual memory for the upper 32 kilobytes of the 16-bit address space. Now, the thing is, let me maybe remove all this here. Now, if I then when I boot the Model 1, I end up in BASIC. So how do I launch this? Well, you type in system. Oh man, I have a really bad handwriting here. System, and then you get the question mark. You say prompt 32768, and that actually will then jump right here. Right, so then the PC, the program counter that Tim also mentioned, will basically fetch the first opcode to 1 hex, which, if you remember, is the first assembly instruction of my demo program, load HL with 0 hex 3C00, which actually you can see in little endian order right here. Okay. So basically, the CPU is just the Z80 is just going to fetch the opcode instruction now from my virtual memory. Now, how do I implement breakpoints? And remember, I had this thing. I think it's here. This address. That is where I want to set the breakpoint. So I want to set a breakpoint at this memory location here. Now, at some point, the CPU is going to fetch this location here. So it will say, give me the memory content of 800C. And ordinarily, I would return 20, which is the jump relative instruction that is part of my demo program. But what if I return something different? What, instead of returning 18, instead of returning 20, I return 8? You can make this a trivia question. Anyone know what the assembly instruction is for hexadecimal 18? I feel like a teacher now. Tim. Okay, and the audio is not so good, but I'm assuming you said the right answer. It's actually a jump relative in the opcode. So jump relative will then fetch the next byte at 800D for the offset. What if then I return FE? Well, that's -1. So basically, I inject an endless loop. So I'm not returning the actual code that is in my demo program here. I don't return the actual code, but I return, if I return this here, for address 800C, I return 18, and for 800D, I return FE. I basically return an endless loop, jump to yourself. And that is how I catch the CPU, and basically, as if I have a breakpoint stop, the CPU is still running at full speed. But by injecting this endless loop, I can artificially then pretend as if I'm stopping there. And if I say resume, well, then I just simply, the next time the CPU fetches 800C, I just let it return the actual opcode of my demo program. So now, having this endless loop here, that is actually not what I do. I have a different debug step that also then communicates the value of the registers to the web server running on TRIS-IO. So the problem is similar to like the Matrix, like when in the movie The Matrix, they are in the Matrix and use the phone to call to the real world. So if you have a debug step here, how can you write a debug step that then communicates the values of the registers to TRIS-IO? And that was also a nice idea that Lawrence came up with. And let me just show you the gist here. So whenever you hit a breakpoint, I inject this debug stub here I overlay it with the program you want to debug. And you can see it's a location independent program. So it can be loaded at any address. So basically then if I set a breakpoint at 800C, I would then be injecting first push HL and then load L, H, load H, 255, and then load L from HL. I mean, this looks like totally nonsensical. Why am I doing this? But this load address here is going to create a memory read access to address FF00 plus whatever the content is of H. And that I can intercept in tris.io, and basically I can store it as the value of H. Then it restores HL, it pushes it again, it again loads H with 255, and now I load HL again with, I load L again with where HL is pointing. So basically now I'm doing a read access to FF00 plus whatever the content of L is. So for example, if I see a read access to FF0A, then I know that L must have had the content of A. So the debug stub goes on for quite a bit, and it basically, in this fashion, it transfers the content of every register to the debug stub running in tris.io, and then I can refresh that from the web interface. Well, and this is now the scary part. I'm going to attempt to actually show you this as a live demo on a Model 1 that Tim Halloran gave me some time ago. So this is now a much trickier demo than PocketTris I showed earlier, but let me attempt this. And Pete, now is the time where I'm going to log in from a different Zoom session. So I'm going to change to a different laptop here. And so I just joined from a different Zoom session. If you can do me a favor, please let me in. Thank you. Okay. So I have to be careful. Okay. Step number 1. Step number 2. Screen share. I have to set up a few things, so just bear with me here. Okay. This is, as you can tell, is a complicated setup here. So, so I have now a camera pointing to the Model 1, and okay, hold on a second. Why is this disappearing? I may have to do a setting here. Presets. Story on top, okay. Yeah, I'm not sure why this disappears when I click on this. This is not good. Okay, let me see if I can.
Just shrink the browser window.
Yeah, that's what I'm trying to do. Okay, this might actually work. Okay, so now first step is I have to reattach the butchered Model 1 to the actual Model 1. If this works, I'm going to have beer for the rest of the day here.
Arne, your camera app on the phone disappeared.
Yeah, okay. Thanks for letting me know. And let me... okay. 1 second. I'm setting up Tris.io here. Let me refresh the web interface. So this web page here now, which is basically what Sasha was also using, is now already connected to the Tris.io card. And what I do now is I'm going to turn on the Model 1. Yeah.
Can you start the web the camera app on your phone again?
I did.
No, it shows your desktop background.
Okay.
Like we see your thunderstorm wallpaper.
I know. Well, it doesn't, let me see, it doesn't update here. Oh man. Okay, let me restart this here.
As far as demos go, I think this is probably one of the more intricate ones I've ever been a part of. So this works.
So let me go to the camera app. You see, where's the camera? Here. Okay. Okay. Wow. I think I'm trying to do too much here with the Zoom screen mirroring and then, okay, let me see. Can you see? No. Yeah, but it's, I don't think it, oh, okay, it's very time delayed here. Okay. So let me turn on the Model 1. Yeah, this screen mirror. Oh, yeah. Okay, now you can see it, right? So I'm at the mem prompt. So now I hit enter. There's a huge delay in the video feed. I don't know why that is. Why is it not updating?
You try in the settings, maybe do the bitrate, reduce that a bit.
Okay, here is it. Settings. Okay, let me try this. Okay, camera went off. Camera is back. Oh, okay, maybe I reduced the quality a little bit too much.
Too far.
Too far. Let me maybe take 1 megabit. Come on. Yeah, okay, I think that's...
that was good, actually.
Yeah, there's still a delay, but let's see if this works. Okay, now comes the moment of truth. So I'm typing the system command on the Model 1, and I don't know why it is so laggy here. You can just, I already typed system, but it just shows up in super small delayed here. What? System. And now I'm typing /32768. And now, fingers crossed. I forgot the breakpoint. That's okay. One should have a little post-it note to write down the sequence of steps. So let me redo this here. Sorry about that. I forgot to set the breakpoint. So you may have seen the whole screen flash up. Now you saw, because I didn't set a breakpoint, that is why it just flashed the whole screen on white. So I'm just redoing this now. Okay, so I'm turning on the machine again. Enter. And it's really too bad that there's such a lag in the video feed of the Model 1 here. So I'm already on the prompt and it hasn't even shown. Hello? Oh, that is just... I tried this earlier, and of course this updated beautifully, but now it's just like frozen. But let me restart this again here, because this is so slow that you can't really see anything. Restart this again. Okay, so you can see the prompt. I don't know. System. Actually, now I need to first set the breakpoint here. So that is why I'm doing this weird screen sharing. So let me now put 800C, which is, if you remember, is the breakpoint. So I just hit now the breakpoint in Sasha's front end. And this ended up being sent to the Tris.io web server. So I've now set on Tris.io the, oh gosh. Let me see. Yeah, okay. So now is the really big part. So let me jump into it again. So if I now hit enter, and again, it's taking some time to update. When I hit enter, it jumps to 8000. It runs the first iteration of the loop. And because I set a breakpoint at 800C, I should be seeing, yes. Can you, okay, you have to wait for a couple of seconds here.
Suspense.
For the video to update here. Oh, come on. Yeah, do you see in the top left corner, the solid block? That is now where I stopped the this fill program after the first iteration. So I can now, in the web interface, press refresh here. And actually, you can look, you can see down here, there is the, I'm stopped at this jump relative, not zero. But you can also see the content of the registers here. So HL is at 3C01, which is of course then one next since I incremented HL. BC is 03FF, which is one decremented. And what I can do now is, and I have to move this a little bit down. No, here is, so now I can do single step. So I click on this button here. I can do refresh. So now you can see it jumped now up to the back to the beginning of the loop here. And notice now I'm just about to do another load HLBF. So if I do another single step, then it should on the Model 1 then fill the next character with the solid block. So I can now single step here. Yes, and I see it on the real Model 1. You have to, now the phone went dead. So pay attention to the video stream here of the Model 1. And I don't know why it's such a delay. Come on. Jesus. Let me restart this again here. It's still frozen at this. I need to show you this, you know. Yeah. Okay, can you see now? I mean, if you know a little bit, you can see that there is now 2 solid blocks here because I just did the second iteration of the loop. Now, let me do something else here. Remember that I said at 8006 is, 8007 is this BF character, this 191, which is the solid block. So let me now use Sasha's interface here. I go to 07. And you can see it shows me that there's BF right now. And what I'm going to do is I'm going to change it with 41 hexadecimal, which is, if you remember, and you can see it also updated the assembly. So it says now load HL41. So I basically dynamically through web interface, I updated this virtual RAM. And my screen mirroring again is flaking out on me. But what I'm going to do now is I'm going to continue to single step and just maybe pay attention to the web interface. You will not see anything on the real Model 1. But then when, okay, let me just go through here. Next single step. It's now on decrement BC. Next single step. Load A, B. Next single step. Or A, C, next single step, jump relative not 0. It is not 0, so it should go up again. And now I'm again load HL with 41. So right now you can see I filled 2 blocks and the prompt RAM size, but there's the M here. So if everything goes well with the next assembly instruction, it should then replace the M here with an A. So let me just do one more single step. Yes, and I'm gonna now see if I can zoom in.
You might have to restart that app again. I think the delay is just accumulating.
So this did not work quite as well as I hoped. Yeah, and you can see there are the 2 solid blocks in the top left corner of the screen. You can see the capital A that I just wrote in the one iteration. And I can maybe just resume. And you can see I'm now single stepping with each. You can see how I'm just now doing like continue, and I'm oh Jesus. I'm now filling the screen with A's. I'm just single stepping each loop iteration here. So that's single stepping on a Model 1, on a real Model 1. That's the demo. And it worked. Okay, I'm gonna go back to my main screen here. So because I wasn't sure if this worked, I took a screenshot just to, in case the demo doesn't work, but the demo did work. So I'm quite happy this actually worked. So this is like a badly hacked Tris.io solution. I can tell you that, of course, when the ESP is serving memory, it is really slow. So it's about a factor 10. And there's another issue if you have opcode fetches and RAM write access, then VRAM doesn't work reliably. There must be some timing issues that I haven't figured out. That's also why I do this weird thing to read from FF00 to communicate register contents to the web server. So that is another issue. And I can only debug in the upper 32 kilobytes because that is where I can intercept read-write memory access to this RAM. So what I would like to do for in the future, maybe then Tandy Assembly 22, is maybe to just have a proper debug interface that is maybe FPGA based. It also then runs at the proper speed that can, like SRAM would ordinarily do. This one here, FPGA solution. But what I'm also thinking is, and Tim, I need to get permission for you to do a hardware mod on your M1, but maybe a little hardware mod that also disables the internal RAM and ROM. Because in that case, you could also actually then single step, if basically the external hardware card would also then serve the ROM content, you could also single step through ROM and through RAM on the lower 32 kilobytes. But that would require a hardware mod to disable the internal ROM and internal RAM. And I would need some help, first of all, what this hardware mod looks like. And then Tim, yeah, you have to give me permission to make this mod on your M1. But that's basically the outlook to the future. And that's it. And with 2 minutes over time, any questions? So, well, thanks for listening. And yeah, Lawrence, thanks for your help too. You know, you also spent some time on our Zoom call to figure out a few things.
Yeah, thank you so much. That was important, essential.
Yeah, and just to echo also Sasha's words, Pete, thanks for setting this up that we could still give our presentation remotely. That was definitely nice. Okay, then feel free to post questions on Discord if you have any follow-up questions. I'm gonna also listen to the last presentation on YouTube, but I guess we're gonna sign off then from this Zoom call here. So you guys have a nice Tandy assembly.
Enjoy.
But I wonder, does he know? Has it ever felt like this? And I know that you would be here right now if I could have let you know somehow. I guess every rose has its thorn, just like every night has its dawn. Just like every cowboy sings a sad, sad song. Every rose has its thorn. Though it's been a while now, I can still feel so much pain. Like the knife that cuts through the wound heals, but the scar, that scar remains. I know I could have said hello that night if I'd known what to say. Instead of making love, we both made a separate ways. And now I hear you found somebody new, and that I never meant that much to you. To hear that tears me up inside, and to see you cuts me like a knife. I guess every rose has its thorn.
Test, test, 1, 2, 3, test. Seems all right.
Has its dawn. Just like every cowboy sings a sad, sad song. Every rose has its thorn. I've tried before to tell her of the feelings I have for her in my heart. Every time that I come near her, I just lose my nerve as I've done from the start. Every little thing she does is magic. Everything she do just turn me on. Even though my life before was tragic, now I know my love for her goes on. I have to tell the story of 1,000 rainy days since we first met. Picking up umbrella, but it's always me that ends up getting wet. Every little thing she does is magic. Everything she do just turn me on. Even though my life before was tragic, now I know my love for her goes on. I resolved to call her up 1,000 times a day and ask her if she'll marry me some old-fashioned way. But my silent fears have gripped me long before I reach the phone, long before my tongue has tripped me. Must I always be her? Every little thing she does is magic. Everything she do just turn me on. Even though my love before was tragic, now I know my love for her goes on. Every little thing she does is magic. Everything she do just turn me on. Even though my love before was tragic, now I know my love for her goes on. since we first met. It's a big enough umbrella, but it's always needed time. Marvin, he was a friend of mine, and he could sing a song. His heart in every line. Marvin sang of the joy and pain. He opened up our mind, and I still can hear him say, oh, talk to me, so you can see what's going on. Say you will sing your song forevermore, evermore. Gonna be some sweet sounds coming down on the night shift. I bet you're singing proud. Oh, I bet you're full of pride. Gonna be a long night. It's gonna be alright on the night shift. You found another home. I know you're not alone on the night shift. Oh, you found another home. I know you're not alone on the night shift. Jackie, hear what you're doing now. It seems like yesterday when we were working out. Jackie, oh, you set the world on fire. You came and gifted us. Your love, it lifted us higher and higher. Keep it up, and we'll be there at your side. Oh, say you will sing your song forevermore, evermore, evermore. Gonna be some sweet sounds coming down the night shift. I bet you're singing proud. Oh, I bet you're full of pride. Gonna be a long night, alright. On the night shift, you found another home. I know you're not alone on the night shift.
Attention in the room. The final presentation is starting now. Please take your seats. Thank you.
I bet you're singing proud. Oh, you're singing proud. Oh, I bet you're full of pride. Oh, yeah. Gonna be a long night. Gonna be alright. On the night shift. On the night shift. You found another home. I know you're not alone.
All right. Thank you, Mr. DJ. All right. Don't worry. I know I'm the last thing between you and our delicious dinner buffet, so I will try to hold this at least 45 minutes, give or take. Welcome to my talk, all about the cocoa. So we haven't heard a lot of technical information about the cocoa with a little brother of the TRS-80 line, perhaps. But there's pretty good cocoa representation at the tables. Hopefully there'll be some people here that are interested. And maybe if nothing else, maybe somebody online like you. All right, so maybe I should start my timer. There we go. So, where are we at? All right, introduction. So who am I? That's an old picture, but that's a good one though, right? I think it looks good. Am I this guy? This is a this is a little joke that went around the community a year or two ago, and some people think that might be me. That's my face, but or am I this guy? The Dark Lord of the Cocoa Realm. Ooh, coming to get you, Bruce. Maybe it's more like this. This is Farv. He's a character from my game Farfall. I like to think of myself this way. Look, I wore my red shirt. So, but really, who am I? Well, so I am a serious computing professional. I work for a well-known company that you probably heard of. So I was initially attracted to the Cocoa in my adult life for serious retro computing. Of course, I had a Cocoa as a kid, so that was the background. But when I came back, I was interested more because I discovered there was some pretty serious things the Cocoa could do that I didn't know about when I was a kid. And when I had my freshly minted computer engineering degree, I wanted to explore some of that. But that's kind of the past. So now I'm more interested in writing games and doing what I call art projects. So things where stuff moves or makes some noise or has lights or whatever. That's really more what I'm into these days. I'm also one of the founders of the Cocoa Crew podcast. Any Cocoa Cruisers out there? A couple, very good. All right. So what is this? So all about the cocoa. That's what day rate cocoa means. It's kind of an academic buzz, not really buzzword, but it's something that you see in old academic papers or whatever. But it just means literally about the thing, the cocoa, right? So we're going to talk all about the cocoa, but it's mostly just going to be almost exclusively about the Cocoa and Cocoa 2 platform. So if you want to know more about the Cocoa 3, come talk to me later. And this will be from a programming perspective, mostly. There'll be some hardware information, but it's more about how could you use that to do your own projects and maybe write programs that use hardware that do stuff, whatever. Also, this presentation is sort of, I don't know, testing the waters, maybe gauging interest a little bit. I don't know what could be a bigger project. I don't know, maybe we'll go into that later. But so if you like the project, let me know, give me some feedback. If you like the presentation, let me know what questions you have or what parts you think I did well on, and of course, what parts you think I totally bombed on. All right, so the Cocoa has always been a great platform for programming. If you use a Cocoa, you probably agree, right? But in BASIC. Nothing wrong with BASIC, but it's basic, right? It's pretty basic. The name is right there in the name. So the color BASIC, that's the BASIC on the Cocoa, also the BASIC on the Dragon, and essentially the BASIC on the MC10. Either way, it hides a lot of hardware details. You don't really have to know much about the hardware to write programs in BASIC, right? Which is sort of the point. So new programmers often don't really know what to do with the hardware. I think this is one of the key things when people start trying to learn assembly language. If you ever try to learn assembly language, there's any given assembly language, you got 4 dozen commands to learn, right? Not really that difficult. They're all pretty simple, but it's not really about the language. It's about what are you trying to do, right? So you got to know, I need to set the hardware to do this and whatever. That's what you're really working on when you're trying to program an assembly language. You're really trying to drive the hardware. So I'm hoping there's some potential assembly language programmers out there. Maybe a little walk through the hardware, how it works. Maybe that alleviates some anxiety. All right, so let's talk a little bit about the Cocoa architecture. We'll start with the chipset. So the CPU of the Cocoa is, of course, the Motorola 6809. I know there's a lot of Z80 fans in the audience. The 6809 is a bit different. This is a diagram lifted from the programmer's manual, I think. Anyway, so the basic architecture, you have the accumulators. There's an A and a B on top, and the A and B are each 8-bit. They can be combined to a 16-bit D accumulator. You can do some 16-bit math operations, add and subtract, that sort of thing. There are a couple of index registers, X and Y. Obviously, these are used for setting up addresses or whatever. There's not just one, actually, there's 2 stack pointers. This can be useful, particularly as a technique for the 6809 called stack blasting, which you basically use one stack to pull in registers and the other stack to push them back out. It can be a pretty efficient way to move memory. But anyway, there's the normal system stack register, which works about like the stack register on any CPU. And then there's a U stack for a user stack, but it has essentially the same kinds of semantics. So you have to figure out on your own when you're programming how that's useful. I did tell you one, the stack blasting, but it's there. Also, both U and S can also be used as 2 more index registers. So for memory addressing, that sort of stuff. And then of course, there's the program counter. Hopefully you have some idea. That's what controls where you are executing your program, of course. And there's a flags register, condition code register. The one down there in the bottom left, the direct page, if you're familiar with the 6502, the 0 page, which is a way to put memory in a kind of a special place where it's a little quicker to access. The direct page is sort of the same idea, but you can point at any given page of memory so that you can move stuff around. And either because you have more than one area that you want to be able to quickly access, or because there's one area you want to favor over and for some whatever reason. Sometimes people will point that to IO block. It's kind of frowned upon, but you can do it. Anyway, there you go. Any simple questions here? Probably not. Just an overview. Let's see, moving on. So the 6847 video display generator provides video output. Let's see. So the clock in is at the chroma burst rate. So it's NTSC video is what's intended for. Oddly enough, even the PAL versions of the Cocoa still use the NTSC VDG when they just add some circuitry around it to fake out PAL or whatever. Anyway, so it gets to the NTSC clock. So they hook it up in kind of a strange way. 6847 has address lines and data lines, and it's supposed to drive for video access, right? But in the Cocoa, the address lines are basically not connected. Just because the SAM actually does the addressing. So there's one address that's connected, the A1 or A0 is connected, and it is used as sort of as a clock to keep synchronization with the SAM. We'll get there in a second. So the VDG has mode control lines. It's actually the configuration of the video chip is externally controlled in the lines. There's 2 lines that are connected to the data bus. And so one of them is for choosing between alpha and semi-graphics modes. And then there's another one for inverting the text. And so you'll see that in some programs where it's actually the data coming off the bus when you access memory that's putting the chip into the different modes. It's kind of a clever way, and that way you can mix semi-graphics and alphanumerics very easily just by changing the data. Let's see, and then the other control lines are a port off of one of the PIAs, the peripheral interface adapters. Also get there in just a second. Okay, here's a sample. This is text in the SG4 mode, semi-graphics 4. Very distinctive look to this. I've spotted probably half a dozen computers just looking at stuff and say, hey, that looks like the Coco. Turns out it'll use the same video chip. So very distinctive here. So this line, the difference between this line of text and that line of text is that the 6-bit is turned on, and that's what tells the VDG to invert the video. And then these lines of text have the 7th bit turned on, which say be in the semi-graphics mode, and then that interprets the rest of the bits differently, which part of which is the color and part of which determines the shape. So, okay, so here's another mode. This is one of the pure graphics modes. This is CG6, which is takes up 6K in memory. This is CSS0. So the 6847 has 4 colors in the graphics modes. There's also 2 color graphics modes, but in the 4 color graphics modes, the palettes are fixed but you can select between 2 fixed palettes. One of them is this red, green, yellow. Very beautiful mode, don't you think? And then here's this is half the resolution, but with the alternative color palette. This is a screenshot from Xmas Rush, which is available on my table as a cartridge. If you're interested, come and see me sometime later. All right, so here's semi-graphics 12, and this is an earlier version of my game Farfall. Took this from somebody's website, but anyway, also the CSS that switches between the different color palettes, it also affects the text mode, so that you can see here the text is basically dark orange on light orange instead of being dark green on light green. Let's see. The CSS pin is one of those that's on that port of the PIA, so it can be externally modified with a write to the PIA. Okay, let's see, yeah. So moving on to the SAM, stands for Synchronous Address Multiplexer, and it kind of glues the rest of the system together. So the SAM controls DRAM, so it does DRAM refresh. It does basically all the address decoding. So the different chips that are available, the SAM is what actually selects them. It also controls the clock input to the CPU. There's a couple of options. So you can have, so you start at that 3579545, NTSC color burst clock. And you can either divide by 4, so there's 0.89, whatever, that goes to the CPU, or you can turn it to half, so it's double the speed, so it's 1.79 or whatever. Now, there are some restrictions there. Basically, it only works when you're running out of ROM, if you just leave it on. If you're running out of RAM, then it will mess up your video accesses. So you can do it, but you have to be careful about it and do it. You can turn it on when you're in the vertical refresh mode, but you need to turn it back off before you show video again. Anyway, so there's this piece of glue logic is in the SAM. Let's see. So the main job of the SAM is it integrates with the VDG and to share a DRAM between the VDG and the CPU. So it kind of, like I said, it kind of helps to keep the system coherent. The VDG and the SAM together in a system actually enable extra video modes. SG8, SG12, which I showed earlier, SG24. And basically this is possible because the VDG is not actually accessing memory. The SAM is accessing memory. So you tell the SAM where your memory's at, and it goes off and gets stuff. You tell your SAM how big the memory is. So it goes off and accesses memory and puts it on the data bus, synchronized with when the VDG is expecting it. So the VDG is waving its arms, saying, I want video, I want this address, the next address, whatever. But it can't actually access the video because it's not connected. But the SAM is out there on this, on the system's behalf, accessing memory and putting it on the data bus, so it works. It's kind of cool. Anyway, because of this and the way the VDG works, basically you can lie to the SAM about what mode you're in and tell the VDG that you're in a different mode. And so the VDG just said, okay, give me the next piece of data. And the SAM goes off and gives him something that the VDG would not have selected, but it works. And so that's why you get these extra video modes. It's pretty cool. Okay, so rounding out the chipset, there are two PIA, peripheral interface adapter chips. Let's see, they each have two bidirectional 8-bit digital I/O ports. The directionality of the ports can be programmed. So I guess they're not technically bidirectional per se. You pick whether each bit is input or output by programming the chip. Anyway, so they're bidirectional in that sense. There are two 1-bit interrupt inputs, so you can trigger interrupts to the CPU with those. And then there's two more 1-bit peripheral control registers or signals. And those are used, well, primarily they're used for setting up the 4-way switch, which we'll talk about in a little bit. But anyway, so the PIAs together are used along with the various hardware constructs, so the other stuff on the motherboard. And together they implement all of the various peripherals that are part of the COCO. We'll talk about that in a bit. So, all right, so the first construct, probably the most important, is a 6-bit DAC or digital to analog converter. So it's typical R to 2R, R-2R. How do you pronounce that? R2R. Anyway, it's a resistor ladder. Nothing really special about the construction. That's a little snapshot out of the service manual. If you want to create one yourself for some reason. Anyway, that's there for the COCO. It's the six most significant bits at address FF20. And these will output a voltage range from 0.25 to 4.75 volts. Just so you know. Primarily used for audio input in one form or another, and this includes for output to the cassette port, so for saving data or whatever programs. Let's see. Okay, 4-way switch is a very important part of the of the COCO architecture. See, it's a dual 4-channel analog mux. One side selects which audio output is output to the RF modulator, so the system sound. The other side selects which joystick access is being fed to the comparator, and we'll talk about the comparator in a minute as well. But so, thing is, both sides switch at the same time based on the same select signals. And so you need to take some care. If you're making any noise as part of your program, particularly like a game, for example, and you want to switch a joystick axis so as to read player input, you can create pops and other kind of noise artifacts as you switch things around, depending on what selections you're making and how you're making the sound, and what various techniques you're using for producing sound. So you need to be aware of that, and you'll probably notice if you're ever doing it. But you need to, like I say, you can take some precautions. The best precaution is don't make any noise while you're pulling the joysticks. All right, so like I said, we're talking about the joysticks. There's a comparator. There's a pretty simple comparator circuit here. It's just that's cut and pasted from somewhere on the internet. But basically, the comparator is what enables software to turn the DAC into an ADC, so an analog to digital converter, which is what's used to sample the joystick axes. So you set the output of the DAC as a reference voltage, which goes to one side, and the MUX output is connected to one of the joystick axes that goes to the other side. And so the comparator output basically tells you which one is bigger. It's pretty simple, right? So software then has to drive the analog to digital conversion through successive approximation, and whether that's a logarithmic operation or a linear operation. Some prefer the linear because they're afraid that the logarithmic doesn't work somehow. Anyway, software uses the DAC plus a comparator to be able to do ADC for sampling the joysticks. All right. So the zero crossing detector shows that there's another comparator connected to the cassette audio input, and it's fixed to compare at 1 volt. And so because it's at 1 volt, which is pretty low, it essentially tells you whenever the analog signal crosses 0. Right? Really it's telling you when it crosses 1, but close enough. And so by counting the number of 0 crossings over some period of time, that gives an indication of the frequency of the input. And you can read that at bit 0 of FF20. So you can use this to discriminate different tones. And so what are some of the applications besides cassette input? So one that's pretty well known is used in the audio spectrum analyzer cartridge available for the Coco. Steve Bjork's best game, if you ask me. But let's see. You can also do radio facsimile. Anybody got a yacht and need to keep weather reports while they're at sea? I don't know. Some people do, I guess, right? I've heard of people doing a software modem, a slow one, 300 baud or whatever. I can't find the code, but I've heard that it's out there, right? So maybe. And could you receive Morse code this way? Seems like you could. So I don't know. Maybe if you want to write a Morse code, maybe this is something that you could use. All right. So here's my eye chart. So there is the cartridge port sitting out on the bus. It is, well, it's largely an interface to the 6809 processor chips, but not exactly. So there are certain signals that are not available. The VMA, I think, is one. But there are a lot of signals that are, and then there's some that aren't directly related to the processor. So we do have the halt line. You can halt the CPU from the cartridge port. There's an NMI line, non-maskable interrupt. NMI is used on the Coco as part of the data pump circuit or data pump program for reading from the floppy drive. Interestingly, the Dragon, which is essentially the same machine from the UK, doesn't use NMI, but it does use halt, so whatever. There's a reset line. So there's, I guess, two phases to or two separate clock signals. There's a quadrature clock for the 6809. So there's two signals. So it's E and Q. Those are both available on the cartridge port. So there's a line called CART, which is tied back through the PIAs and is used to generate an interrupt at the CPU. There's a line on the cartridge port called CTS. It's cartridge select is what it's supposed to be, and this is the chip select that targets the ROM on a cartridge for the Coco. So that's basically for reading that ROM. SND or sound is a line that directly connects the line on the cartridge into the audio mixer that feeds out to the RF modulator on the Coco. So if you have a piece of hardware that wants to generate audio, it uses this line. All right, so there's SCS. Now this is kind of like CTS. SCS stands for spare cartridge select. I didn't name it. But instead of being intended for selecting the ROM on a cartridge, it's really intended for selecting other hardware on a cartridge. And so, for example, on the Coco floppy disk controller, CTS selects the ROM on there, whereas SCS selects the actual floppy control chip. Right? Let's see, and then there's one more that's kind of important, kind of confusing. If you ever want to design complicated hardware for the Coco, I recommend that you study the schematics until you figure out how this one works. SLIN-B. So I'll just read off the chart here. This signal disables the internal device selection, so allows decoded but unused sections of memory to be used by cartridge hardware. And so this is basically, if you want to have hardware that plugs into the Coco, and especially if you want to overlay an address that's actually used by internal hardware on the Coco, or there's some other reasons to use it. But basically, this basically feeds back into the Coco and says, okay, turn off your address decoding. I've got it. And so you're responsible then for fully decoding the address lines of the Coco. This, from the 6809. Anyway, if you want to talk about SLIN-B, come see me tomorrow. All right. So there's, of course, a keyboard provided by a switch matrix connected to PIA ports on one of the PIAs. There's two PIAs on board. One of them is largely dedicated to the keyboard. So you have eight column lines attached to the PIA port at FF02. These are outputs. And then you have 7 rows attached to the PIA port at FF00. These are configured as inputs. So when you want to scan the keyboard, you bring one column low at a time. So there's your sequence. You write FE or then your FD or FB. You notice these are basically a walking zero if you want to decode them, or you can trust me. And so you write out that on your keyboard, your column outputs. You read back your row inputs, and if any of those are low, it indicates which key has been pressed. And so you have to know what the matrix says, but that's how it works. Let's see. So I mentioned that the Dragon is essentially the same machine. The Dragon folks are following the same reference design published in the SAM data sheet. So they're eerily similar machines overall. But for whatever reason, probably a legal reason, they decided to modify the keyboard matrix. But they didn't do much. Basically, they took exactly the same columns, same rows per column, and then they just took and said, okay, we're going to take this column, we're going to put it here. So literally, If you wanted to hack a Coco keyboard into a Dragon keyboard, you could basically do it with a pair of scissors. I'm pretty sure that would work because it's a flex cable on the Coco 2 and the Coco 3. Anyway, so interesting note. Okay, so here's the joystick. I just put up again, this is a snapshot from the service manual. I just put up the schematic because it's probably the easiest way to talk about it. There's not a lot to the Coco joysticks. Basically, you have two variable resistors, one for each axis. They're mounted in a gimbal. That means a little joystick thingy. Right? And they both feed back from the center tap to a pin on the joystick port. One of the pins on the joystick port is +5. That goes to one side of each of those. The other one, of course, comes to ground. So these are voltage dividers, right? If you've had the most introductory electrical engineering class of anything, you've heard of a voltage divider. That's how they work. They are 100K potentiometers if you can find a way that it matters. For the most part, it's just that they're voltage dividers. And, you know, if you're sucking a lot of power, I guess it could matter. So don't put too low of a resistor out there or a potentiometer. But anyway, that's most you see this a lot because a lot of other systems, particularly the Apple II, the IBM PC, they had analog joysticks, so they had potentiometers mounted in a gimbal, but they used a different system for reading them. They used a timed RC circuit. And in those cases, you know, the C, the capacitor is on the motherboard in the Apple II or whatever. So your R better be the right value or else your time's going to be wrong for whatever position you want to be in. But you don't have to worry about that if you're doing a Coco joystick. Just don't suck enough power to kill the system and you'll be fine. Anyway, one more thing, there is a switch on the Coco joysticks. On the original, you know, as I call them, Black Beauty joysticks. That was my term first. Everybody else stole it from me. There's one big red button on the front. On some of the later ones, there's two buttons. It's basically the same circuit, just another line. On the 2-button joysticks, instead of the one line going to pin 4, there's another line that goes to the pin in the middle. But anyway, we're not talking about that now. But as you can see, it's just a switch. It takes that line to ground. Pretty standard way to implement physical input on the system from the era, shall we say. All right, so moving on to the cassette interface. This is an audio interface designed around 80s era consumer tape decks. Hopefully we're all familiar with those. I can show you one if you want. But, you know, I know being my age, I remember being a kid, having one thing that was pretty cool, carrying around the tape deck. But then you could plug them into your computer too. Bonus. So you get output from the Coco, from the 6-foot deck on the Coco, and this goes out a cable to the tape deck. The input comes back in and is fed to the zero crossing detector so that you can detect the tone frequencies. There is a PIA controlled relay, so there's one bit on one of the PIAs that energizes a relay. And this goes to the remote circuit. And on these old tape decks, they had a remote circuit that basically plugged these two wires together, and it turns on the power to the tape deck. This is how your Coco is able to turn the tape deck on and off. Essentially plugging it in and out. I don't know, I think it's funny. Okay, that was it for that. Okay, so there's the other port there, the RS-232 bit banger. These uses pins hanging off of a PIA So the serial port is driven by software using the PIA pins for signaling. There's one output pin. This is used for transmit. There's two input pins. One's used for receive. The other one is ostensibly for carrier detect. Each of these pins has a circuit, a level translation circuit that that adapts the TTL levels inside the Cocoa to RS-232-ish levels. On the original Cocoa 1, I think they were up until plus and minus 12. On the Cocoa 2, I think it's plus and minus 5, something like that, or maybe plus 5 and, I don't know exactly. I'd have to look it up. But anyway, they're close enough to RS-232 for it to be useful. Now, this is software driven. So bitbang.io, it's prone to missing incoming characters. If you're not listening when they come, you're probably going to miss it. Generally limited to 300 bits per second max. Just a second there. Mr. Boise Pete's going to talk about a technology tomorrow that makes use of the bitbanger in a clever way that allows you to go a little faster, mostly because the Cocoa never has to wait unless it's asked. It's already asked for the data, so it knows when to wait. Anyway, that's neither here nor there. All right, so there is a little side note. There's an op amp that's used for the transmit level shift on the Cocoa 1, and it is the default one is slower than the salt chip, which was the custom chip from Tandy. So serial and level translator is what it stands for. That's was on the Cocoa 2 and 3. This is why you'll see some technologies out there will differentiate by how fast you can go with a bitbang serial port. You can go faster on a Cocoa 2 than a Cocoa 1. You can go faster on a Cocoa 3, but that's mostly because it can be clocked faster. But anyway, you can also pop out the op amp and put in a faster one on a Cocoa 1 and get the faster speed. All right. Let's see. Okay, PCM audio. I'm not going to go into a lot of detail, but this is one of the peripherals on the Cocoa. You can do PCM audio, pulse code modulation. Literally, you take samples of a waveform, put them on the DAC, you recreate the waveform with your sample values, and you make sound. Anyone have any questions about PCM? Pretty simple, I think. All right. Okay, there is a 1-bit, some call it a beeper. Basically, it's one PIA pin, the setup as an output, and it is hooked into the audio output circuit. And so it gets mixed in, and you can drive that. There's bit 1 of FF22. You can drive that to make noise. Now, interestingly, this is not routed through the 4-way mux. It's kind of off to the side. So you can put your mux selection wherever you want it and still produce sound this way, which means this is one of the other options. If you want to make noise at the same time that you're switching the joysticks, sampling the joysticks, if you're making noise with the beeper, shouldn't be affected when you switch the mux. So let's see. So anyway, so this 1-bit audio source, it's available for CPU-driven 1-bit audio. You can use PCM, pretty coarse, 1-bit PCM, but it's possible. And for simple tones, it's not so bad. For sample, if you've got a Cocoa, try the sound command. That gives you an idea of what it sounds like. Terrible, but serviceable. One of the earlier presentations mentioned PWM, pulse width modulation, PDM, pulse density modulation. You can do both of those, whichever one you like, whichever one you understand well enough to implement. You can do those with a 1-bit audio as well. All right, sources of interrupts. So hardware interrupts are a useful means of synchronization with real world events. So if something happens, need to know about it for whatever reason. So Coco has several interrupt facilities that might be useful for your application. So there's the NMI input on the cartridge port. I mentioned earlier, this is used for synchronizing the data pump on the floppy drive controller or for accessing the floppy drive controller. Probably not a perfect solution for every application, but it works pretty well there, mostly. There's an IRQ line. So I should have mentioned this when we're talking about the 6809. The 6809 has two different types of interrupts. It has the traditional IRQ interrupt. So when this happens, the CPU automatically stacks all the registers and jumps to the IRQ vector. Now there's also what's called a fast IRQ or FIRQ, which is a separate line. When that triggers, the CPU doesn't stack any registers, or it stacks the register, the PC, like it's making a, because it does a jump to the FIRQ vector, but it doesn't stack any of the other ones. And so A, it doesn't take the time to stack them, and then B, if you wrote your handler correctly, you either don't have to stack any or you only have to stack what you're actually using. So it's faster, right? So anyway, so it's tied to one of the PIAs, and that PIA takes has its interrupt inputs. One's for VSync from the VDG, one's for HSync or horizontal sync on the VDG. So these are related to television signaling, right? So VSync is when you get to the bottom of the screen, you got to go back up. HSync is when you get to the side of the screen and you got to go back to the right. So VSync happens 60 times a second, almost. HSync happens about 15,500 times a second, a little more than that. Anyway, so they're available. They can be used for pretty reliable timing sources if you account for them properly. And I mean that in terms of real time for, human interaction, that sort of thing. So there is an FIRQ available, but unfortunately it's through a different PIA, tied to so it's tied to a different set of signals. So for example, what always seems ideal to me is it would have been nice if they'd have hooked up the HSync to the FIRQ line, because that happens a lot. And if you try to process, but unfortunately HSync and VSync both go through the one tied to IRQ. And so if you try to process HSync interrupts, you spend so much time stacking registers and unstacking registers that by the time you've done that once, you've already missed, you're ready for the next IRQ, or at least you're into the next period. Now there's somebody who does code for the Coco that is actually taking advantage of that. And so they've essentially they do essentially a HSync divided by 2 timing. And so they just deliberately miss the HSync period and come back on the second time around so that they can use that. And so it's a 7,500 hertz. Is that right? Yeah. Give or take. I think that's pretty clever, but anyway, it's something you can do if you need to. So again, back to FIRQ. So this is connected to the cart signal, which if you remember is through the cartridge port. So if you have a piece of hardware that you want to write an application for that could take advantage of, especially if it can take advantage of this faster timing source, put it on the cartridge and you can use cart and it's available. Also, you can hook up the CD line, the carrier detect line from the RS-232. I don't think this is practical for any normal use of RS-232, but maybe. I don't know if there is a normal use of RS-232, to be honest. A lot of various standardized things, but traditionally carrier detect would literally be the modem turned on Well, do you really need the fastest interrupt available to say the modem turned on or the modem turned off or whatever? No, but it's there. Maybe you can use it. All right. So we're right at 45 minutes. I've got a couple of scenarios I thought I'd walk through. Maybe you'll bear with me. So video mode selection. Here's another chart, another snapshot from the service manual. But when you want to select one of these video modes, so alphanumerics, inverted, semigraphics, different modes. Excuse me. All right. Here's your chart, and there's two parameters here. There's one for the bits that you write to the PIA register, which is what you think would be the main thing, kind of the main thing. But then there's also these bits that are set at the SAM. Now the SAM, like I said, the SAM has a heritage as a DRAM controller, and I know I've seen this in other DRAM controllers. When you want to program configuration bits in the SAM, you actually do that by doing kind of dummy memory accesses to certain addresses. And you'll have, I don't know them off the top of my head, but you can look them up. So that's what these V1, V0, V1, V2, these are some of those bits, and you set them a certain way in the SAM. Let's see, can we see this on the graph? 128 by 96 versus SG12. Yeah, so here's the one for 128 by 96, color graphics, 100. Well, then SG12, same settings. And so this is what I was telling you. You basically lie to the SAM about the mode that you're in so that it goes off and accesses memory as if it's a certain size and feeds the data to the VDG, which of course will be, it'll think it's in semigraphics mode, which is set by the data you're giving it back, or it's essentially in an alphanumeric mode. But so anyway, so that's how the magic's done. If you're really interested and can't figure it out, contact me. I'll be happy to walk you through it. All right, so that's video mode selection. Here's an example, some assembly code. Like I said, the memory accesses for setting up the 001 here. I think you can do stores instead of clears, but I like clears better. Anyway, so these even addresses clear the bits. An odd address sets the bit. And then you set up a value and store it to the PIA. And then you do the same kind of thing for setting the base address, which the SAM needs to know for moving the window around in memory. So pretty simple assembly language. Can't teach you assembly language right now, but I promise you, if you learn some 6809 assembly language, that's simple. All right, so how do you plot pixels? All right, so here's another little snapshot from a service manual. But so here's a byte of data. Oops, sorry. This is a byte of data in a 4-color mode. So you can see you got C1, C2, so that's 2 bits for 1 pixel. Another 2 bits, another 2 bits, another 2 bits. So 4 pixels per byte. How do you plot them? So for one thing, the most significant bits will be the farthest left on the screen. It's good to know. So you're locating a pixel in terms of X, Y's. Fairly simple math. You start at the screen base address. You multiply Y by your line width in bytes. Like 32 bytes is typical. Depends on the mode. Then you take X modulo the number of pixels per byte. So X modulo 4. And add that. And there's your byte address. And so then you modify the relevant bits in that byte for whatever pixels you want to, and then you write it back. Pretty simple, right? Now you know how to write graphics to the Coco. Okay, so here, more assembly language. So this is what you do when you're reading a joystick. This is the mode selection code was taken from Xmas Rush, by the way. The joystick code is taken from Farfall. So it is real code. It actually this is setting up the PIA. Setting up the PIA to select the right-left access for the left joystick. So left to right. So once you've set that up, you write a value to the DAC. That feeds one side of the comparator. This comparator is the axis of the joystick. So, so you feed in the DAC, you access the comparator bit, and based on whether it's set or not, you know whether or not, you know, where you are on the joystick, basically. And so here I've got a value that's 65 hex, that's what, 101. And 98 hex is what, 128, 140, 152. So basically I'm testing the axis and leaving a dead zone in the middle so that you don't have, if you're not properly centered or whatever, you don't necessarily move. But so that's how it works. You can kind of follow the jumps around. But so if you want to read the joysticks on the Coco, it looks something like that. Now you'll also see people or code examples that instead of picking a couple of places, they'll start it either at 0 or, well, 4, I guess, but or they'll start at a high value and they'll walk by ones or whatever. I don't think you should do that. I prefer the logarithmic approach, but depends on you. All right, so how do you play music on the Coco? All right, so you can do 1-bit PCM, PWM, or PDM. You can do 6-bit PCM. You can do cassette port playback, so you can actually have an external audio source. You can have a synthesizer on the cartridge. My Farfall cartridges have a synthesizer on them if you want to hear what that sounds like. $40. Anyway, so let's just review. We don't want to write code for this right now, right? So you select your audio source with the 4-way mux if necessary. And if you're using the 1-bit audio, you don't have to do this, right? Otherwise, you need to select either the DAC or the cassette or the cartridge. You need to enable audio output at the mux. Again, you don't have to do that with a 1-bit DAC. You need to set up any timing sources. If you're going to be doing synthesis on your own, you're going to need some kind of fine timing for audio, for the tone generation, for literally creating the waves. And then you probably need a coarser timing for changing notes. So typically that would be H-sync based on the fine timing and V-sync based on the coarse timing. Or maybe you write your own loops and count cycles. That's up to you. All right. And at this point, you either start the cassette, you turn on the synthesizers, or you jump to the code and start synthesizing. Pretty simple, right? All right, so conclusion, the Coco, love her. The Coco remains a rich and rewarding computing and gaming platform for many to this day. I'm one of them. A couple others of us here feel the same way, I think. So with this peek on the inside, here's your challenge. What can you make the Coco do for you or for all of us? Okay. So, any questions?
I think I understand what you said. I'm assuming on the interrupts for VSync and HSync, like HSync continues through the vertical blanking interval and just stop.
On the Coco, on the NTSC Coco, the chip itself does continue with the HSync. And so you can continue counting HSyncs even while it's VSync or whatever. It seems that some of the PAL implementations, I'm not sure about for the Cocoa, but for the Dragon, there are some that seem to cut it off, which is a little weird, but they do. And that'll mess up if you're synthesizing in software. That'll mess you up. Well, whatever. What it really will do is, for the most part, it'll make a buzzing sound. So you'll still kind of hear the tone because it's there most of the time, but there'll be these interruptions, and it'll sort of be a buzz.
How do you do page flipping, or like what are you doing to get carefree graphics when you have the video modes and things like what's going on?
Well, so typical would be to monitor VSync and do whatever drawing you need to do in VSync, and/or you can set up a different page. And so in VSync, you could flip to the other page, which is a sequence of accesses to flip those bits in the SAM, so that the SAM will start fetching from the new page. But basically, you would do that in a VSync time, generally speaking. So.
How different is this architecture compared to the OC10?
Wow, completely different, really. I mean, you have the VDG is theoretically the same, but it's configured separately. For example, the address pins on the MC10 are configured, which is why the MC10 video buffer starts at 0. and they didn't even move it. It's just right there at 0. Of course, the CPU on the MC10 it's a 6803, which is a derivative of the 6800. More so than the 6809. It's technically a derivative of the 6800, but the 6803 really is a 6800 with a couple of extra instructions, and there's some more nuance in that, but it's a different chip, not binary compatible or anything. And like I said, so there's no SAM. So you have a fixed video buffer. You don't have the SG8, SG12, SG24 video modes. You still have SG4 because that's part of the chip, and there is SG6, which is a little bit hobbled because of the way they're using the data bits for indicating video modes. I can go into more detail if you're really interested, but anyway, it is way different. I mean, they're kind of similar. If you want to stick to basic, they're pretty similar, but if you actually want to do machine code, they're way different. So, anyone else?
What would you suggest to someone that wants to get back into programming for basic and working assembly? What would you suggest would be a good start?
Well, basic is a great place to start. You don't have to know much about the hardware, and it's pretty forgiving on syntax and that sort of thing. If you do want to do assembly language or whatever, probably would pick up something like the Barden book if you want to be used on the Cocoa, and kind of pull through some of those exercises. Now, unfortunately, the Barden book, of course, targeted the EdTASM cartridge, and which is okay for the time. Today, I wouldn't use the cartridge. Some people do. Today, I wouldn't use it just because. Who was it earlier? Someone was talking about how much better it is to use modern tools, and it's just so much better to use modern tools that I don't know that I would advise it. But if you're literally learning about how to do stuff, then it's a walk before you can run kind of thing. So, like I said, I'd probably pick up the Barden book. There was a couple others. There's one from Lawrence Tepolt. It's a blue book. It's kind of the same level as the Barden book, so you might check that one out. Or you might have a lot of fun flipping through old Rainbow magazine articles and checking. They ran a lot of tutorial articles back in the day, so you might flip through some of that.
What process assembly?
Typically, I use LWSM these days. I did use one that Boise had derived a variation on the old Motorola freewheel assembler that he called Memu, which is kind of an inside joke. There's at least one other 5809. It's pretty good. Just sort of, it's all assembly language. So it depends on what you're doing. If you want to use some of the macros, code or whatever, or some of them have different outputs or different pseudo ops for including data or whatever. But they're kind of, to some degree, they're all the same, right? If they're not, then they're not working. Anyway, but LWSM works pretty well for me. It seems to work for a lot of people. So, anyone over here? Okay. All right, I think that'll conclude us. Thank you very much. Oh, let's see. I can be contacted. And of course, please listen to the Cocoa Crew podcast. Okay. All right, thank you.
Okay, everybody, these chairs and everything, they're going to set up some round tables here for the dinner here. If you're a Tech Track attendee, or if you have a table here, you are authorized to enjoy the meal here. They're going to bring it in here, and we should be ready to eat here in 15 or 20 minutes. Thanks.
Be happy. Don't worry, be happy. Don't worry, don't do it. Be happy. Put a smile on your face. Don't bring everybody down like this. Don't worry. It will soon pass. Don't worry, be happy. I'm not worried. I'm happy.
Jesse is a friend. Yeah, I know he's been a good friend of mine. But little girl, I wanna make her mine. And she's watching him, and she's loving with that body. I just know it. And he's holding her in his arms late at night. You know, I wish that I had Jesse's girl. I wish that I had Jesse's girl. Where can I find a woman like that? I'll play along with the charade. There doesn't seem to be a reason to change. You know, I feel so dirty when they start talking cute. I wanna tell her that I love her, but the point is probably moot. Cause she's watching him with those eyes, and she's loving him with that body. I just know it. And he's holding her in his arms late at night. No, I wish that I had Jesse's girl. I wish that I had Jesse's girl. Where can I find a woman like that, like Jesse's girl? I wish that I had Jesse's girl. Where can I find a woman? Where can I find a woman like Jesse's girl. Well, it's alright, riding around in the breeze. Well, it's alright, if you live the life you please. Well, it's alright, doing the best you can. Well, it's alright. You consider everything. Wonder what tomorrow will bring. Maybe a diamond ring. Well, it's alright, even if they say you're wrong. Well, it's alright. Sometimes you gotta be strong. Well, it's alright, as long as you got somewhere to lay. Well, alright, every day is Judgment Day. Maybe somewhere down the road away, you'll think of me and wonder where I am these days. Maybe somewhere down the road when somebody plays Purple Haze. Well, it's alright, even when push comes to shove. Well, it's alright, if you got someone to love. Well, it's alright, everything will work out fine. Well, it's alright, we're going to the end of the line. Don't have to be ashamed of the car I drive. I'm just glad to be here, happy to feel that. And it don't matter if you're by my side, I'm satisfied. Well, it's alright, even if you're old and gray. Well, it's alright, you still got something to say. Well, it's alright, remember to live and let live. Well, it's alright, the best you can do is forgive. Well, it's alright, riding around on the breeze. Well, it's alright, if you live the life you please. Well, it's alright, even if the sun don't shine. Well, it's alright, we're going to the end of the line.
I only knew you for a while. I never saw your smile till it was time to go, time to go away. Sometimes it's hard to recognize love comes as a surprise, and it's too late. It's just too late to stay. Too late to stay. together, together in electric because the friendship that you gave has taught me to be brave. No matter where I go, I'll never find a better prize. Though you're miles and miles away, I see you every day. I don't have to try, I just close my eyes. I close my eyes. We'll always be together, however far it seems. We'll always be together, together in electric dreams. We'll always be together, however far it seems. We'll always be together, together in electric dreams. We'll always be together, however far it seems. We'll always be together, together in electric dreams. We'll always be together, however far it seems. We'll always be together, together in electric dreams.
Here she come now, say morning, morning. Shoot 'em down, turn around, come on, morning. Hey, just give me love and I feel alright now. You gotta toss and turn and feel alright, and I feel alright. I say yeah, 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 yeah. 'Cause you make me feel so good, so good, so good, so fine, so fine. It's alright. Well, I feel alright. I say yeah, 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 yeah. Well, you get shaking, moaning, moaning. Shotgun dead and I'll come on moaning. Don't stop cooking, I feel alright now. Hey, don't stop now, come on moaning, come on, yeah. I say yeah, 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 yeah. God, you make me feel so good, so good. Well, I feel alright, so fine, you're so fine, you're so fine. I don't feel alright, yeah, 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 yeah. I love you more than Yeah, 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 yeah. Come on, 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 feel alright. I said, yeah, 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 yeah. Wake it, shake it, moan it, moan it. Up, down, turn around, come on, moan it. Hey, she give me love and I feel alright now. I said, don't stop now, come on, moan it, come on, moan. I said, yeah, 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 'cause you make me feel so good, so good, so good, feel alright, alright, so high, well, I feel alright, yeah, 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 yeah. I wanna ride the pony, ride the pony, ride the pony. Come on, come on, come on, ride the pony, feel alright. I said, yeah, 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 'cause you make me feel so good, so good, so good. Come on, yeah, alright. Well, it feels so good. I said, yeah. I can't fight this feeling any longer, and yet I'm still what started out as friendship has grown stronger. I only have strength to let it show. I tell myself that I can't hold out forever. I say there is no reason for my fear, 'cause I feel so secure when we're together. You give my life direction, you make everything so clear. And even as I wander, I'm keeping you in sight. You're a candle in the window on a cold, dark winter's night. And I'm getting closer than I ever thought I might. Then I can't fight this feeling anymore. I've forgotten what I started fighting for. It's time to bring this ship into shore and throw away the oars forever. 'Cause I can't fight this feeling anymore. I've forgotten what I started fighting for. And if I have to crawl upon the floor, come rushing through the door, I can't fight this feeling anymore. My life has been such a whirlwind since the Lord. I've been running around in circles in my mind. And it always seems that I'm following you, girl. But you take me to the places that alone I'd never find. And even as I wander, I'm keeping you in sight. You're a candle in the window on a cold dark winter's night. And I'm getting closer than I ever thought I'd like. And I can't fight this feeling anymore. I've forgotten what I started fighting for. It's time to bring this ship into the shore. Throw away the oars forever. 'Cause I can't fight this feeling anymore. I've forgotten what I started fighting for. If I let you crawling on the floor, come crashing through your door, baby, I can't fight this feeling anymore. All the old paintings on the tomb, they do the sun dance, don't you know? If they move too quick, oh well, they're falling down like a domino. All the buzz on men by the Nile, they got the money on a bet. Old crocodiles, oh well, they snap their teeth on your cigarette. Foreign types with the hookah pipe say, oh well, oh well, oh well. Walk like an Egyptian. The blonde wits around and they cross the floor. They've got the move. You drop your drink, then they bring you more. All the school kids so sick of books, they like the punk and the metal band. When the buzzer rings, oh well, they're walking like an Egyptian. All the kids in the marketplace say, well, 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 well. Walk like an Egyptian. Slide your feet up the street, bend your back, shift your arm, then you pull it back. Like it's hard to know who's on a Cadillac. If you wanna find all in the donut shop, they sing and dance. Oh, way, oh. They spin the club cruise down the block. All the Japanese, the Italian, the party boys call the Kremlin, and the Chinese know. Oh, way, oh. They walk the line. Egyptian, all the cops in the donut shop say, walk like an Egyptian, walk like an Egyptian.
my mind set on you, but it's gonna take money, a whole lot of spending money. It's gonna take plenty of money to do it right, child. It's gonna take time, a whole lot of precious time. It's gonna take patience and time to do it, 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 to do it right, child. I got my mind set on you. 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 And this time I know it's real. The feeling that I feel. I know if I put my mind to it, I know do it. I got my mind set on you. Set on you. I got my mind set on you. Set on you. But it's gonna take money. Whole lot of spending money. It's gonna take plenty of money to do it right, child. It's gonna take time, whole lot of precious time. It's gonna take patience and time to do it, 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 to do it right. I got my mind set on you. 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 And this time I know it's real. The feelings that I feel. I know if I put my mind to it, I know that I really can do it. But it's gonna take money, a whole lot of spending money. It's gonna take plenty of money to do it right, child. It's gonna take the time, a whole lot of precious time. It's gonna take patience and time to do it, 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 to do it right.
Just a small town girl living in a lonely world. She took the midnight train going anywhere. Just a city boy, born and raised in South Detroit. He took the midnight train going anywhere. A singer in a smoky room, a smell of wine and cheap perfume. For a smile they can share the night. It goes on and on and on and on Streetlights, people, living just to find emotion, hiding somewhere in the night. Working hard to get my fill. Everybody wants a thrill. Paying anything to roll the dice just one more time. Some will win, some will lose. Some of them just sing the blues. Oh, the movie never ends. It goes on and on and on and on. Strangers waiting, looking down the boulevard. Their shadows searching in the night. Streetlights, people, living just to find emotion, hiding somewhere in the Don't stop believing. Hold on to that feeling. Streetlight people. Don't stop believing. Oh, no. Streetlight people. Don't stop believing. Hold on to that feeling. Streetlight people.
Life is a mystery. Everyone must stand alone. I hear you call my name, and it feels like home. When you call my name, it's like a little prayer. I'm down on my knees. I wanna take you there in the midnight hour. I can feel your power, just like a prayer. You know I'll take you there. I hear your voice. It's like an angel sighing. I have no choice. I hear your voice. Feels like flying. I close my eyes.
Hello, everybody. Our meal is ready, so you can make your way over to the buffet, and we have tables set out here, the round tables. So help yourself to some food and have a seat.
Touch the flame where the streets have no name. I wanna feel sunlight on my face. Disappear without a trace. I wanna take shelter in the poison rain where the streets have no name. Where the name, we're still building and burning down, burning down. And when I go there, I go there with you. It's all I can do. The city's afloat, and our love turns to rust. We're beating the blood. Wind trampled in dust. I'll show you a place high on a desert plain, where the streets have no name, where the streets have no name. We're still building and burning down. And when I go there, I go there with you. Oh, I can do. I want to see us. We're beating the blowing of the wind, blowing by the wind. Oh, yes, see don't have to pay rich to be my girl. You don't have to pay school to rule my world. I just want your every time, yo. Women like to rule my world. They rule my world. Shoes off, lady. You don't have to watch fantasy to have an attitude. You just need it all to be my love will be your food. Yeah, you don't have to be rich to be my girl. You don't have to be cool to rule my world. I just want your every time, yo. She don't even know my name, but then she asked me just the same. Studio. She called me, I'll be there. I'll come running anywhere. She's all I need all my life. I feel so good if I just say the word. So studio. Just say the word. Oh, so studio. Now I know that I'm too young. My life has just begun. So studio. Oh, give me a chance, give me a sign. I'm so ready time. Studio. Oh, I've got to have fun now. Got to get closer, but I don't know how. She makes me nervous, makes me scared. I feel so good if I just say the word. So studio. Just say the word. So studio. She's all I need all my life. I feel so good if I just say the word. So studio. I just say the word. Hey, little girl, is your daddy home? Did he go and leave you all alone? I got a bad feeling. Ooh, I'm on fire. Tell me now, baby, is it good to you? And can he do the things that I do? I can take you high. Ooh, I'm on times like someone took a knife, baby, edgy and dull, and cut a 6-inch valley through the middle of my soul. At night I wake up with the sheets soaking wet and a freight train running through the middle of my head. When I was a young boy, slipping with those young boy ways. Now that I'm getting older, so much older, I long for those young boy days with a girl like you, with a girl like you. Lord knows how things we can do, baby. Just me and you, come on, let's so good. Come on, baby, make it hurt so good. Sometimes love don't feel like it should be, baby. Hurt so good. Don't have to be so excited. Gotta give myself a little bit of fun. I always look so excited. You're in the street and you are young. Hey, baby, it's you. Come on down now, you. Think I'll creep right through my bones, baby. Let's see what we can do. Come on and take it up. What's so good? Come on, baby, make it hurt so good. Sometimes love don't feel like it should, make it hurt so good. I ain't talking no big deal. I ain't made no plans myself. I ain't talking no high heels. Baby, we can move around all day long. Walk around all day long. What's so good? Come on, baby, make it hurt so good. Sometimes love
Don't feel like it's too late. Let's go to love. Let's go to love. Come on, baby, now. Come on, baby, make it hurt so good. Sometimes love don't feel like it's too late. Let's go to love.
Night is very clear. We're both lying here. There's so many things I wanna say. I will always love you. I would never leave you. Sometimes I just forget. See things I might regret. Breaks my heart to see you cry. I don't wanna lose you. I could never make it. I am the man who will fight for your honor. I'll be the hero you're dreaming of. We'll live forever, knowing together we feel all the glory of love. We're standing tall, hoping through it all. I'm always on your side. I have always needed you. I could never make it. I am the man who will fight for your honor. I'll be the hero you've been dreaming of. We'll live forever, knowing together we feel for the glory of love. Like a knight in shining armor from a long time ago. Just the time of the season day, we can do my God so far I am the man who will fight for your honor. I'll be the hero that you're dreaming of. We're gonna live forever, knowing together
Remember the things that you do. It's the rain, I'm still in love with you. Miss you like crazy. Miss you like crazy. Everything you with away. Every hour, every day. I miss you like crazy. I miss you like crazy. No matter what I say or do, there's just no getting over you. I can see the love shining in your eyes. How you love me inside. You say you believe so soon. Hold me as starting forever now. I miss you like crazy. I miss you like crazy. Everything you will away. Every hour, every day. I miss you like crazy. I miss you, baby. Love like I will never be. Just like the end of just one night, and we'll have the night to feel it like we used to. Hold on tight, and whatever comes our way, we're gonna make it through. Things that evening is worth the wait. Hold me and tell me it's not too late. Hold us together, starting forever now. 'Cause I miss you like crazy. I miss you like crazy. No matter what it takes, let's just go get it on with you. And I miss you, I miss you. All the things of love you gave me. And the feeling gets it so. It's all the real things come along, and I miss you. I miss you like crazy, baby. All the young things I can say. I miss you like crazy. I love like I've never. Just let me understand again. Miss you like crazy. Falling down in a dead man's town. The first kick that took us while I hit the ground. End up like a dog that won't be too much. See you stand half your life to cover it up now. Born in the USA. Born in the USA. Born in the USA. Born in the USA.
Shadows of death, declare in the room that the liberation and relief. Hey now, don't believe it's over. Hey now, the world comes in, let on, oh, between us, just let on win.
would walk 500 miles an hour, would walk 500 more. Just a hate of my would walk 1,000 miles and all that you know. Working up a place. Come on, girl, let's go on the side that we know how to be number one in the hot show. Push it good. Push it real good. Push it good. Push it real good.
Sunset dreaming that it never ends. As long as you're gone, we may as well pretend I've been dreaming. Straight from the heart. You say it's crazy, but who's to say that we'd be able to keep it this way? But it's easier when it's straight from the heart. Oh, give it to me straight from the heart. Tell me we can make now a start. No, I'll never go. As long as I know I'm in. You won't be from others, and all I was get all I was feeling. Straight from the heart. Oh, give it straight from the heart. Tell me we can make one more start. No, I'll never go. As long as I know I'm in straight from. Straight from the heart. Tell me we can make one more start. No, I'll never go. As long as I know. Straight from the heart. Tell me we can make one more start. No, I'll never go. As long as I know. I'm in straight from the heart. Give it to me. Oh, yeah. Oh, no. Straight from the heart. No, I'll never go. As long as I know I'm in straight from the heart. But I couldn't find a way, so I said the whole world. Tell me lies, tell me sweet little lies. Tell me lies. Oh no, no, you can't disguise. You can't disguise. Tell me lies, tell me sweet little lies. And though I'm not making sense, I hope that you understand. No more broken hearts. We're better off. Tell me lies, tell me sweet little lies. Tell me lies. Oh no, no, you can't disguise. You can't disguise. Tell me lies, tell me sweet little lies. If I could turn the time that I feel just a big but I couldn't find it. So I'll settle for one thing. Tell me lies, tell me sweet little lies. Tell me lies. Oh no, no, you can't disguise. You can't disguise. Tell me lies, tell me sweet little lies. Tell me lies. Oh no, no, you can't disguise. You can't disguise. Tell me lies, tell me sweet little lies.
For a while, standing there with her hands in her hair, I can't help remember just when she touched me. There's still no place here in her place. So cool, she was like dazzling someday. Music, high and sweet, then she just flew away. Now she can't be that one with the wind in her arms. Follow me, call on me, call on me. Follow me, come and see me. I'm the same boy. Love songs fill the night, but they don't tell it all. Not how love the cry, just like that I used to cry. And that in time, somewhere, someday, some good may go on back to me. Some night, I mean, oh, like she used to be. No, it can't be that one with the wind in her arms. Follow me, call on me, call on me. Follow me, come and see me. I'm the same boy to be. I
She can't see that warm with the wind in her arms. Not a breeze. Come on me, come on me. Come and see me. I'm the same boy I used to be. Makes me forget that. Great, great wine. It's up to you. All I can do, I said, make me just one thing makes me forget. Great, great wine. Stay close to me. Don't let me be in love. Scary fun. Just one thing makes me forget. Great, great wine. Stay close to me. Don't let me be in love. Scary fun. Nothing else. Great, great wine. Stay close to me. Don't wish it away. Don't look at it like it's forever. Between you and me, I could honestly say the things can only get better. And while I'm away, just down the demon inside, and it won't be long before you and me run. Please never harm. Will we hide? And I guess that's probably calling up. Time on my hands, since I've been with you. Love you like children, living like lovers, rolling
happy in your hand. Live for every second without hesitation. Never forget of your plan. Without me, girl, crying night in hell. Mama, hell, I simply love you more than I love life itself. And I guess that's why they call it the blues. Time on my hands, the time spent with you. That's just like children, living like lovers, rolling like thunder under the covers. And I guess that's why they call it the blues. Children, living like lovers, rolling like thunder under the rubber. And I guess that's why they call it the blues. And I guess that's why they call it the blues. And I guess that's why they call it the blues. And I guess that's why they call it the blues. Well, I'm all back down, so I won't back down. You could stand me up at the gates of hell, but I won't back down. No, I'll stand my ground, won't be turned around. And I'll eat this world from dragging me down, but I stand my ground, and I won't back down. Hey, baby, there's no easy way out. Hey, stand my ground, and I won't back down. Well, I know what's right. I got just one life in a world that keeps on pushing me around, but I'll stand my ground, and I won't back down. Hey, baby, there ain't no easy way out. Hey, stand my ground, and I won't back down.
O'clock already, I was just in the middle of it. I was kissing Valentino by a crystal blue Italian stream. But I can't be late, so then I guess I just won't get paid. These are the days when you wish your bed was already made. It's just another manic Monday. Wish it was Sunday. That's my fun day. I don't have to run day. It's just another manic Monday. Have to catch an early train. Got to be to it by 9. And if I had an airplane, I still couldn't make it on time. 'Cause it takes me so long just to figure out what I'm gonna wear. Blame it on the train, but the bus is already there. It's just another manic Monday. Wish it was Sunday. That's my fun day. I don't have to run day. It's just another manic Monday. All of my nights, why did my never have to fit last night to get down? Last night, doesn't matter that I have to be the conquerors and Gorman's down. He tells me in his bedroom voice, come on, honey, let's go make some noise. Time it goes so fast. It's just another manic Monday. Wish it was Sunday. That's my fun day. I don't have to run day. It's just another manic Monday. Wish it was Sunday. You see, I haven't been the same since that cold November day. We said we needed space, but all we found was an empty place. And the only things I learned is that I need you desperately. So here I am, and can you please tell me, oh, where do broken hearts go? Can they find their way home? Back to the open arms of a love that's waiting there. And if somebody loves you, won't they always love you? I look in your eyes, and I know that you still care for me. I've been around enough to know that dreams don't turn to gold, and that there is no easy way. No, you just can't run away. But we have so much more than we ever had before. And no matter how I try, you're always on my mind. So here I am, and can you please tell me, oh, where do broken hearts go? Can they find their way home? Back to the open arms of a love that's waiting there. And if somebody loves you, won't they always love you? I look in your eyes, and I know that you still care for me. Now that I am here with you, I'll never let you go. I look into your eyes, and now I know, where do broken hearts go? Can they find their way home? Back to the open arms of a love that's waiting there. And if somebody loves you, won't they always love you? I look in your eyes, and I know that you still care. But when you broken hearts go, can they find their way home? Back to the open arms of a love that's waiting there. And if somebody loves you, won't they always love you? I look in your eyes, and I know that you still care for me. For me. You still care for me. Call you, I need you, my heart's on fire. You come to me wild and wild. You come to me, give me everything I need. Give me a lifetime of promises and a world of dreams.
love like you know what it means. It can't be wrong. Take my heart and make it strong. You're simply the best. Better than all the rest. Better than anyone. Anyone I've ever met. I'm stuck on your heart. I hang on every word you say. Tears apart. Baby, I would rather be dead. In your heart, since the start of every night and every day. In your eyes, I get lost, I get washed away. Just as long as I'm here in your arms, I could be in no better place. You're simply the best. Better than all the rest. Better than anyone. Anyone I ever met. Ooh, I'm stuck on your heart. I hang on every word you say. Oh, tears apart. No, no. Baby, I would rather be dead. Each time you leave me, I start losing control. Walking away with my heart and my soul. I can feel you even when I'm alone. Oh, baby, I know my
Tumble out of bed and I stumble to the kitchen. imagination and yawn and stretch and try to come to life. Jump in the shower and the blood starts pumping. Out on the streets, the traffic starts jumping with folks like me on the job from 9 to 5. Working 9 to 5, what a way to make a living. Barely getting by, it's all taking and no giving. They just use your mind and they never give you credit. It's enough to drive you crazy if you let it. 9 to 5, for service and devotion. You would think that deserve a bad promotion, want to move ahead, but the boss won't seem to let me in. I swear sometimes that man is out to get me. They let you dream just to watch him shatter. You're just a step on the boss man's ladder, but you got dreams he'll never take away. In the same boat with a lot of your friends, waiting for the day your ship will come in and the tide's gonna turn and it's all gonna roll your way. Working 9 to 5, what a way to make a living. Barely getting by, it's all taking and no giving. They just use your mind and you never get the credit. It's enough to drive you crazy if you let it. 9 to 5, yeah, they got you where they want you. There's no better life, and you think about it, don't you? It's a rich man's game, no matter what they call it. And you spend your life putting money in your wallet. 9 to 5, oh, what a way to make a living. Getting by, it's all taking and no giving. They just use your mind and they never give you credit. It's enough to drive you crazy if you let it. 9 to 5, yeah, they got you where they want you. There's no better life, and you dream about it, don't you? It's a rich man's game, no matter what they call it. And you spend your life.
I had a friend was a big baseball player back in high school. He could throw that speedball by you, make